When people hear the word light, they usually think of brightness, color, or speed, something fast, something weightless, something that doesn't quite behave like ordinary objects. That instinct is close to the truth, but it misses the role light plays in physics. Light is not treated as a material object moving through space. It is treated as a way energy travels. And the moment you take that seriously, light stops being special in a mystical sense and starts obeying the same accounting rules as everything else. The first important point is this: light has no rest mass, but it does carry energy and momentum. Those two facts together explain nearly everything that seems strange about it. Momentum is often associated with heavy things, cars, balls, planets. But in physics, momentum depends on energy and motion, not just mass. Light moves at the fastest speed allowed by nature, and because of that motion, its energy automatically comes with momentum. When light hits a surface and reflects, the surface experiences a force. It is small, but it is real. Instruments measure it. Spacecraft designs account for it. Something without mass can still push. This already tells us something important about mass itself. Mass is not simply how much stuff there is. In physics, mass measures resistance to acceleration and how strongly something interacts with gravity. Light cannot slow down or speed up, so resistance to acceleration doesn't apply to it in the usual way. But gravity still affects light. Light bends when it passes near massive objects. Stars and galaxies change its path. This happens not because light secretly has mass, but because gravity is not just a pull on mass. Gravity describes how space and time are shaped, and anything that moves through space and time follows that shape, light included. That leads to a deeper connection. Mass and light are not opposites. They are different ways energy shows up. Mass is energy arranged in a form that can remain at rest. Light is energy that cannot stop moving. When matter emits light, it loses a tiny amount of mass. When matter absorbs light, it gains a tiny amount of mass. This is not a metaphor. It is a measurable effect predicted by physics and confirmed by experiment. The amounts are usually too small to notice, but the exchange is exact. Seen this way, light becomes easier to talk about. It is energy moving freely with no option to slow down. And mass becomes energy arranged in a form that can stay put. Both follow the same rules. They differ not in nature, but in how that energy is allowed to behave. And accepting that mass and light are both ways energy exists naturally leads to a more basic question. What is light itself at the most fundamental level? Most people start with an intuitive picture. Light feels like something that travels from place to place, almost like an invisible stream. That picture works well enough to turn on a lamp or aim a flashlight, but physics needs something sharper. In physics, light is not defined by brightness or color. Those are experiences produced by our eyes. Light is defined as an electromagnetic disturbance that carries energy and momentum through space. That phrase sounds abstract, so it helps to ground it in something familiar. Think about a lake. If you drop a stone into water, nothing travels from the center of the splash to the shore. The water itself mostly stays where it is. What moves outward is the disturbance, the changing height of the surface. Light behaves in a similar way, except the surface is the electromagnetic field, and the disturbance moves through space. Space in physics is filled with electromagnetic fields. These fields are not made of material. They are properties assigned to every location. Just as temperature can have a value everywhere in a room, electric and magnetic fields have values everywhere in space. Light appears when these field values change over time in a linked way. A changing electric field produces a magnetic field. A changing magnetic field produces an electric field. Those changes sustain each other and propagate forward. That traveling pattern is light. Nothing physical is being carried along like a thrown object. What moves is the change itself. This already challenges common sense. Everyday experience trains us to expect motion to involve objects. Light forces physics to deal with motion without transport of matter. That is why light does not need a medium. Sound needs air, because sound is motion of air molecules. Light is motion of fields, and the fields are already present everywhere. Now, intuition usually pushes back at this point and says, fine, but light still feels like a particle. That instinct is not wrong, but it needs refining. Light is often described in terms of photons. A photon is not a tiny glowing bead flying through space. A photon is the smallest unit of electromagnetic energy that can be exchanged. It becomes relevant when light interacts with matter. A famous experiment makes this unavoidable, the photoelectric effect. When light shines on a metal surface, electrons can be ejected. Classical intuition predicts that brighter light should knock electrons out more easily, regardless of color. That prediction fails. Experiments show that if the light's frequency is too low, no electrons come out at all, no matter how intense the light is. Increase the frequency past a threshold, and the electrons appear immediately, even at low brightness. This behavior makes sense only if light transfers energy in discrete packets. Each photon carries a specific amount of energy set by its frequency. If that energy is too small, no amount of piling photons together helps. Common sense expects gradual buildup. Nature does not allow it here. That experiment forces a conclusion. Light behaves as packets of energy during interaction. But light also spreads, bends, and interferes, behaviors that match waves. The same phenomenon shows wave behavior during travel and particle behavior during exchange. That is not contradiction. It is a limitation of everyday categories. At a deeper level, light is described as a quantized excitation of the electromagnetic field. The field can only change by certain allowed amounts. Light corresponds to those allowed changes moving through space. Now mass enters the picture again. Mass appears when energy becomes locked into arrangements that can persist. Electrons bound to nuclei, fields tied together, motion constrained. That trapped energy behaves as mass. Light represents energy that is not trapped. This explains why light has no rest mass. Rest mass is defined as energy present when an object is not moving. Light cannot meet that condition. There is no reference frame in which light stands still. The idea of rest simply does not apply. Because of that, light always travels at the same speed, not because it is pushed and not because it chooses that speed, but because electromagnetic field equations permit only one speed for self-propagating disturbances. That speed is built into space and time. This challenges another intuition. Speed usually depends on how hard something is thrown. Light ignores that rule entirely. This is also why light defines the maximum speed anything can have. Objects with mass must be able to slow down or stop. Light cannot. That difference separates matter from radiation. Color now fits naturally. Color corresponds to the frequency of the electromagnetic oscillation. Higher frequency means higher energy per photon. Lower frequency means lower energy per photon. The energy of light is tied directly to how rapidly the field changes. This explains why ultraviolet light can damage cells while radio waves cannot, even if the radio waves deliver more total energy. Each ultraviolet photon carries enough energy to alter chemical bonds. Radio photons do not. Common sense expects total power to matter most. Physics shows that how energy is packaged matters just as much. Another famous example reinforces this: gravitational lensing. Light bends as it passes near massive objects, not because light has mass, but because gravity shapes space and time. Light follows that shape because it always follows the geometry of space-time. Photographs of distant galaxies warped by gravity confirm this behavior directly. Light responds to gravity, even without mass. That fact forces physics to abandon the idea that gravity is simply a pull between masses. It is something deeper. Light can push because momentum comes with energy in motion. Light bends because space-time guides all energy. Light carries information because fields can vary in organized ways. Light heats objects because energy transfer alters atomic motion. No special rules are required just for light. It follows the same accounting as everything else. Light is energy in its most mobile form. It cannot remain still, cannot gather into stable structures, cannot pause. Mass is energy arranged in forms able to persist. Both arise from the same underlying quantity, governed by the same rules, behaving differently because the universe permits them. Understanding light this way removes mystery without removing wonder. It becomes one of the cleanest examples physics offers of how energy, mass, space, and time belong to a single connected system. At this point, light stops being just something that lets us see and starts becoming a guide to how reality is organized. Because light does more than move energy, it sets limits. It defines connections. It tells space and time how they are allowed to behave. One of the most surprising consequences is this: light determines what can influence what. In everyday thinking, cause and effect feels simple. Something happens, then something else responds. Distance just means delay. Farther away means later. That intuition works well for walking across a room or throwing a ball. Light exposes where that intuition breaks. Nothing that carries energy or information can act faster than light. Not because light is special in a sentimental way, but because it represents the fastest way any physical influence can move through space and time. Light draws the boundary between what can be causally connected and what cannot. This has a concrete meaning. An event can only affect another event if light has time to travel between them. If it cannot, then no physical signal, no force, no message can bridge that gap. This limit is not about technology or engineering. It is built into how electromagnetic fields and space-time behave. That boundary shapes the structure of time itself. Events are not simply ordered by before and after in an absolute sense. For distant events, the order can depend on motion. What remains fixed is causality, whether one event can influence another. Light sets that rule. This is why light sits at the center of relativity without being introduced as an extra idea. Relativity does not say, light is special, so everything must obey it. It says, the rules of space and time are such that light emerges as the universal speed that everything agrees on. Common sense expects time and space to exist first, with light moving inside them. Physics finds the opposite. Light reveals how space and time are stitched together. Another implication follows directly from this. Because light carries energy and momentum, but has no rest mass, it shows that mass is not the fundamental currency of physics. Energy is. Mass is one way energy can appear. Light is another. This relationship is captured exactly in the connection between mass and energy. When matter emits light, its mass decreases. When matter absorbs light, its mass increases. This is not an analogy, it is a measurable fact. Nuclear reactions make this visible on large scales, but the same exchange happens whenever light is involved, even in ordinary processes. This forces a revision of how substance is understood. Objects feel solid, permanent, self-contained. Light feels fleeting. Physics shows that both are arrangements of the same underlying quantity. The difference is not what they are made of, but how long the arrangement can last. This leads to a result that feels strange at first. Empty space filled with light has inertia. A box filled with light weighs more than the same box without it. The difference is tiny, but it exists. Energy contributes to gravity, regardless of whether it appears as mass or radiation. That result is not intuitive. Common sense expects weight to come from matter. Light refuses to cooperate with that expectation. Another deep consequence appears when information enters the discussion. Light is the primary way information moves through the universe. Every image, every signal, every measurement relies on light or electromagnetic radiation in some form. That is not an accident. It follows from the fact that electromagnetic fields can change in structured ways and carry those changes across space. This means information is physical. It is not abstract. It has energy costs. Sending a message requires energy. Detecting a signal requires energy. Even learning something leaves physical traces in matter. Light connects information to energy in a way that cannot be separated. This connection also explains why observation matters so much in physics. To observe something is to exchange energy and information. Light is almost always involved. Observation is not passive. It is an interaction governed by the same rules as everything else. This removes a common misunderstanding. Physics does not say reality depends on human awareness. It says reality depends on physical interaction. Light makes those interactions possible across distance. There is also a deeper unity hiding here. Light obeys quantum rules when exchanging energy. It obeys relativistic rules when moving through space-time. It obeys classical rules when large numbers of photons act together. The same entity connects three major frameworks of physics without changing identity. That alone is remarkable. Many ideas in physics appear to belong to one domain or another. Light refuses to stay confined. It forces theories to agree with one another or be discarded. Any serious description of nature must make room for light behaving consistently across scales. This makes light less like a topic and more like a test. If a theory mishandles light, something is wrong. Finally, there is a conceptual implication that is easy to miss. Light shows that the universe is not built from objects alone. It is built from relationships, constraints, and allowed motions. Light is not a thing traveling through space so much as a way space and time allow energy to move. That idea changes what existence means in physics. To exist is not only to occupy space, it is to participate in the rules that govern change. Light participates fully. It carries energy, momentum, information, and influence. It connects distant regions of the universe while obeying strict limits. It reveals that those limits are not obstacles, but the structure itself. Seen this way, light is not mysterious. It is honest. It tells us exactly how far causes can reach, how energy can travel, and how space and time cooperate to make events possible at all. Understanding light deeply is less about learning new facts and more about accepting that the universe is organized by rules that feel unfamiliar yet remain consistent everywhere. So, after all of this, it's worth asking what picture of the world actually remains when the details settle. Light in physics is not a special case and not an exception. It is a reference point. It shows how energy behaves when it is free to move, how space and time respond to that motion, and how limits arise naturally from the structure of the laws themselves. What we know with confidence is this. Light is an excitation of the electromagnetic field. It carries energy and momentum. It always moves at the same speed because the equations that describe the field allow no alternative. It has no rest mass, yet it responds to gravity because gravity governs space-time, not just matter. It transfers energy in discrete units during interaction, which explains experiments that classical intuition could not. These statements are not speculative. They are supported by measurement, technology, and repeated observation. We also know that mass and light are not separate categories of substance. They are different behaviors of energy. Mass corresponds to energy arranged in forms that can persist. Light corresponds to energy that cannot be held still. Both contribute to gravity. Both obey conservation laws. Both belong to the same accounting system. From this, a coherent worldview emerges. The universe is not primarily built from objects. It is built from fields, energy, and constraints on how change is allowed to occur. Objects appear when energy becomes organized in ways that last. Light appears when energy moves freely through fields. Space and time are not passive backgrounds, but active parts of the system determining how motion and influence are permitted. This worldview removes several common misunderstandings. Light does not travel through nothing. It propagates through fields that are already present everywhere. Light does not behave strangely. It behaves consistently under rules that differ from everyday experience. Light does not blur physics. It forces precision. It also clarifies what we do not yet know. We do not know why the electromagnetic field exists in the form it does. We do not know why the constants that determine the speed of light have the values they do. We do not yet have a complete theory that unifies light's quantum behavior with gravity at the smallest scales. These are active areas of research, not settled matters. But the gaps are bounded. They do not undermine what has already been established. Any deeper theory must still reproduce the behavior of light exactly as observed. The rules light follows are not optional features of reality. They are constraints any explanation must satisfy. That is an important distinction. When people hear space and time, they usually picture two separate ideas. Space feels like the stage where things sit. Time feels like the clock that ticks while things happen. That picture works well for daily life, and it feels natural because experience trains us to think that way. Physics began with the same picture. Early scientists treated space as a fixed grid and time as a universal rhythm. Events took place somewhere, and they happened at some moment. The two ideas stayed politely separate, like coordinates written in different columns. Then careful measurement started to whisper that something deeper was going on. Light turned out to behave in a very peculiar way. No matter how fast an observer moved, light always traveled at the same speed. Walking toward a beam, chasing it in a rocket, standing still on Earth, every measurement agreed. That single fact forced a quiet revolution because speed connects distance and duration. If the speed of light stays fixed, then distance and duration can no longer stay independent. Space and time began to lean into each other. Imagine describing an event. A flash appears, a bell rings, a particle decays. To locate that event, one must give both a position and a moment. Physics discovered that these two pieces of information blend together in a precise way. Change the motion of the observer, and the split between distance and duration changes, while the combined description stays consistent. That combined description receives a single name: space-time. Space-time treats every event as a point with 4 numbers attached to it. 3 describe where, 1 describes when. The surprising part lies in how these numbers relate. Different observers may disagree about distances and durations, yet they agree about the space-time separation between events. Something deeper than space alone, or time alone, holds everything together. This explains effects that once sounded like paradoxes. Moving clocks tick differently. Lengths measured along the direction of motion change. None of this comes from faulty instruments or strange materials. It comes from space-time itself, assigning different slices of distance and duration to different observers. A useful way to picture it involves paths. Every object traces a path through space-time, called a world line. Standing still in space still means motion through time. Moving faster through space tilts that path, trading some motion through time for motion through space. All objects move through space-time. They simply choose different directions within it. This single idea replaces many separate rules. Instead of asking how space behaves and how time behaves, physics asks how space-time behaves. Motion, light, cause and effect all follow from that geometry. Once this viewpoint settles in, the universe begins to look less like a stage with actors and more like a woven fabric where events, motion, and measurement share the same structure. The fabric keeps its own order, quietly guiding everything that happens within it. Once that idea settles in, another shift follows almost automatically. Motion stops being something measured against a fixed background. Instead, motion becomes a comparison between different paths through space-time. Two observers moving differently are not arguing about reality. They are slicing the same space-time in different ways. This is where time stops being universal. There is no single master clock ticking for the entire universe. Each object carries its own time along its path. A wristwatch measures how much space-time that particular path passes through. That amount is called proper time, and it belongs to the object itself. Two observers can separate, move differently, reunite, and honestly report different elapsed times without contradiction. Space-time allows it. This sounds strange only because everyday speeds hide the effect. At human scales, the differences are tiny. At higher speeds, they grow. At the speed of light, something remarkable happens. Time along that path stops entirely. For light, there is no passage of time between emission and absorption. That fact is not poetic. It falls straight out of space-time geometry. Light traces the boundary structure of space-time. It marks the limit of cause and effect. Events outside that boundary cannot influence each other, not because of technological limits, but because space-time itself does not connect them in the right way. Cause and effect are not rules imposed afterward. They are built into the geometry. This also explains why simultaneity loses its absolute meaning. Two events that appear simultaneous to one observer may not appear simultaneous to another. There is no single answer to what is happening right now everywhere. Each observer carries a personal slice of space-time they call the present. The universe does not privilege one slice over another. Once this is accepted, space-time stops feeling abstract and starts feeling practical. Satellites orbiting Earth experience time differently from clocks on the ground. Their paths through space-time differ, so their clocks tick at different rates. Navigation systems must correct for this or they fail. The theory does not live in textbooks. It runs quietly inside technology. Then gravity enters the story, and space-time deepens again. Instead of treating gravity as a force pulling objects together, space-time describes it as curvature. Massive objects change the geometry around them. Paths that once looked straight bend, not because something pushes them, but because straight itself has changed meaning. An object moving freely follows the straightest possible path through curved spacetime. That path is called a geodesic. Falling, orbiting, drifting through space, these are all expressions of geometry, not force. Remove all other influences, and an object simply follows spacetime's shape. This explains why all objects fall the same way, regardless of mass. They are not being pulled differently, they are following the same geometry. The motion comes from spacetime itself. Time feels this curvature too. Clocks closer to massive objects tick more slowly than clocks farther away. Again, this is not mechanical stress or interference. It is geometry assigning different amounts of time to different paths. Space and time no longer act as separate players. They respond together. Mass and energy tell spacetime how to curve. Spacetime tells matter how to move. This mutual relationship replaces the older idea of forces acting across empty space. At this point, spacetime begins to sound less like a background and more like an active participant. It expands, bends, stretches, and evolves. The universe does not sit inside spacetime. The universe includes spacetime as part of its physical content. Cosmic expansion fits naturally into this view. Galaxies move apart not because they fly through space, but because space-time itself grows between them. No central point is required. Every location sees the same pattern because the geometry itself changes. Even emptiness is no longer empty. Space-time can ripple. Gravitational waves are distortions that travel through it, carrying energy and information. Detectors on Earth measure these ripples as tiny changes in distance, smaller than atomic nuclei, yet perfectly real. Georgetown itself vibrates. At this stage, space and time stop being containers and start being relationships. Distances, durations, motion, gravity, and causality all emerge from a single structure. Learning space-time is not about memorizing effects. It is about adopting a new way to organize experience. Instead of asking where something is and when it happens as separate questions, space-time asks how events relate to one another, which events can influence which others, how much change fits along a given path, how geometry shapes possibility. Once seen this way, many puzzles lose their mystery. Slowed clocks, curved orbits, cosmic expansion, limits on signals follow from one consistent picture. Nothing special needs to be added. Nothing hidden needs to be assumed. Space-time does not explain everything, but it explains why so many things fit together so tightly. It provides a language where motion, gravity, and time speak the same grammar. Understanding that grammar makes the universe feel less strange, not because it becomes familiar, but because it becomes coherent. The fabric does not need intention or awareness. Its structure alone guides the unfolding of events, patiently and precisely, everywhere at once. Once space-time is understood as a structure rather than a stage, another quiet consequence appears. Events themselves become more important than objects. Physics stops asking what something is in isolation and starts asking how events connect. A collision, a flash of light, a heartbeat, a thought, each is an event, and space-time organizes how these events relate. This is why space-time cares so deeply about limits. There is a maximum speed, not because motion is difficult, but because space-time geometry allows only certain connections between events. Light sits at the boundary. Anything slower can be influenced by many events. Anything faster would require skipping over space-time itself. The limit is structural, not technological. This boundary shapes reality in a very practical way. It decides what can be known, what can be affected, and what can never be connected. Two events can be close in space, yet unreachable in time. Others can be distant, yet causally linked. Space-time does not measure closeness by meters or seconds alone. It measures it by whether influence can pass. This is where intuition, trained by everyday life, begins to soften. Distance is no longer just how far. Time is no longer just how long. Separation becomes a question of space-time intervals. Some separations allow influence, some forbid it forever. This idea alone explains why the past feels fixed and the future feels open. Events in the past sit inside the region that can influence the present. Events in the future do not yet. That difference is not psychological, it is geometric. Space-time also explains why changing the past remains impossible. It is not guarded by paradox or mystery. The geometry simply does not permit paths that loop back in the required way under ordinary conditions. The structure blocks them. At this point, space-time starts to sound rigid, almost unforgiving. Yet it also allows extraordinary freedom. Different observers carve space-time into space and time differently, and all of them are equally valid. No observer owns the correct present. Each carries a personal frame shaped by motion and gravity. This dissolves the idea of a universal now, replacing it with many consistent viewpoints layered on the same structure. That realization feels unsettling at first, but it actually simplifies things. Arguments about who is right fade away. The rules do not change, only the coordinates do. Space-time itself does not care how it is labeled. Then something deeper emerges. Energy and momentum are not separate bookkeeping tools floating on top of space-time. They are tightly linked to its structure. Motion through space and motion through time are two sides of the same coin. Change one and the other responds. This is why energy, mass, and momentum transform together when observers move differently. Mass turns out to be concentrated energy moving mostly through time. Light turns out to be energy moving entirely through space. Everything else lies between. This is not metaphor. It is how space-time measures motion. This also explains why adding energy to a system can increase its inertia. Resistance to acceleration is not stubbornness, it is geometry reacting to energy content. Once gravity is folded into this picture, space-time becomes dynamic. It no longer sits passively while matter moves. It responds. Energy curves space-time, and curved space-time redirects energy. This feedback loop shapes stars, galaxies, and the universe itself. Black holes appear naturally here. They are not exotic monsters added by imagination. They form when space-time curvature becomes so strong that all paths tilt inward. Not even light can find a route outward. Time itself points toward the center. Near such regions, time slows dramatically relative to distant observers. This is not an illusion. Different paths through space-time accumulate different amounts of time. Clocks tell the truth locally, even when they disagree globally. At large scales, space-time stretches. The expansion of the universe is not matter racing away from a center. It is geometry evolving. Distances grow because the metric itself changes. This allows galaxies to separate faster than light without breaking any rules, because no object outruns light locally. The space between them grows. This distinction matters. It prevents confusion. Motion through space-time and change of space-time are different processes. Both are allowed. Both are measured. Space-time also stores memory. Gravitational waves carry information about violent events long after they occur. When two massive objects merge, space-time rings like a struck bell. Detectors sense these vibrations as tiny shifts in distance. Geometry itself becomes observable. At this stage, space-time stops being abstract. It acquires physical consequences that can be touched, measured, and engineered around. And yet, space-time remains subtle. It does not tell objects where to go. It defines what paths are available. Objects follow those paths not by choice, but because no alternatives exist. This removes the need for invisible forces reaching across emptiness. Motion becomes local and natural. This perspective also clarifies why space-time feels smooth at large scales and uncertain at small ones. On everyday scales, geometry averages out. On extreme scales, quantum effects begin to stir. How space-time behaves when those effects dominate remains one of the great open questions. Still, even without that final answer, space-time already provides a powerful unifying language. It ties together motion, gravity, light, causality, and time into one coherent structure. It replaces many separate rules with a single geometric idea. Learning space-time is not about visualizing 4 dimensions perfectly. It is about recognizing that space and time are aspects of one system that cannot be pulled apart without breaking consistency. Once that recognition settles in, explanations become easier. Effects stop piling up as disconnected surprises. They line up as consequences of structure. Space-time does not explain everything. It does not explain why the universe exists or why its rules take the form they do. But it explains how those rules fit together once they exist. And that is enough to speak about it clearly, to teach it honestly, and to carry the idea forward without mystery or exaggeration. It becomes a way to talk about reality that is restrained, precise, and surprisingly intuitive once the old separations are allowed to fade. At this point, space-time can be treated as a working framework rather than a surprising idea. It becomes a practical tool for organizing physical laws. Instead of memorizing separate rules for motion, gravity, and light, everything fits into a single structure governed by geometry. The key fact to hold on to is this: space-time provides the measuring system for all physical processes. Distances, durations, speeds, energies, and causal relationships are all defined within it. When physics predicts something correctly, it does so because the space-time description remains consistent across situations. This consistency shows up in equations, but it also shows up in experiments. Atomic clocks flown on airplanes return with measurable time differences. Signals from distant spacecraft arrive exactly when space-time predicts they should. Light bends around massive objects by amounts that match curvature calculations precisely. None of these effects rely on interpretation. They are measurements checked repeatedly. Space-time also explains why certain quantities are conserved. Momentum, energy, and angular momentum remain stable because space-time itself has uniform properties. When space looks the same in every direction, momentum is conserved. When time flows uniformly, energy is conserved. These are not coincidences. They are consequences of geometry. This connection makes space-time central to modern physics. Any new theory must respect it or explain why it changes. This applies to particle physics, cosmology, and attempts to unify gravity with quantum mechanics. Even speculative ideas begin by asking how space-time behaves. Importantly, space-time does not remove everyday intuition, it refines it. At low speeds and weak gravity, space-time reduces smoothly to familiar rules. Classical mechanics appears as an approximation, not an error. This explains why earlier physics worked so well before deeper structure was discovered. Space-time also clarifies limits. Faster-than-light communication fails, not because of engineering difficulty, but because space-time geometry blocks causal connections. Absolute simultaneity fails, not because clocks malfunction, but because space-time allows multiple consistent time orderings. These limits are not flaws, they are features that keep physical laws coherent. When teaching space-time to others, the goal is not to force visualization of 4 dimensions. The goal is to communicate relationships. Events relate through space-time intervals. Paths accumulate time differently. Geometry guides motion. Once these ideas are in place, most effects feel expected rather than strange. At the same time, space-time remains incomplete. On very small scales, quantum effects become important, and the smooth geometric picture may break down. How space-time behaves under those conditions is still under investigation. Current theories work extremely well within their tested range, but they are not final. That uncertainty does not weaken space-time's role. It shows its importance. Any deeper theory must recover space-time behavior where experiments confirm it. This requirement narrows possibilities and guides progress. In practice, space-time acts as the backbone of modern physics. It connects experiments on Earth with observations of distant galaxies. It links clocks, rulers, particles, and fields into a single language. It explains why different observers can disagree locally while agreeing globally. Understanding space-time well enough to explain it to others means being able to describe what stays the same when perspectives change. Distances and times vary. Space-time relationships do not. Forces can be reinterpreted. Geometry remains. Measurements differ. Structure persists. That reliability is what makes space-time useful. It allows prediction without appeal to hidden mechanisms. It replaces separate explanations with one consistent framework. Once that framework is clear, space and time stop feeling like separate ingredients of reality. They become aspects of a single system that organizes all physical change. And with that understanding, discussions of motion, gravity, light, and causality naturally fall into place using one shared set of ideas rather than many disconnected ones.
You know, when I was young, I used to take things apart. Radios, mostly. I wanted to see how they worked. What was inside? What made them do what they did? I never really stopped doing that. I just moved on to bigger things. Instead of radios, I started taking apart the universe. And the amazing thing is, the universe lets you. It doesn't hide its secrets, not really. You just have to look carefully, think carefully, test your ideas against reality. The universe is honest. It doesn't lie. It doesn't play favorites. It treats everyone the same.
Why should that be? Why should the universe be comprehensible at all? Nobody knows. But it is, and that's what makes science possible. We are the universe looking at itself. How do atoms, mindless atoms, give rise to a mind, to the feeling of being someone? We don't know. That's one of the great mysteries. So, what is this universe we find ourselves in? It's big. The nearest star is 4 light years away. There are hundreds of billions of galaxies. The numbers are so vast they stop meaning anything. It's old, 14 billion years. If the history of the universe were 1 year, all of human civilization would fit in the last few seconds before midnight on December 31st. We're newcomers. The universe got along fine without us, and it will get along fine after we're gone. That might sound depressing, but I find it liberating. Because despite our smallness, we've figured out so much. A few pounds of gray matter inside your skull, and it can comprehend the cosmos. And the universe follows rules, laws, patterns. The same force that makes an apple fall also keeps the moon in orbit. There's a unity to nature. So, let me tell you something. If all of scientific knowledge were to be destroyed tomorrow, and only one sentence
could be passed on to the next generation of creatures, what statement would contain the most information in the fewest words? I believe it is this, that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. In that one sentence, you see, there is an enormous amount of information about the world, if just a little imagination and thinking are applied. Now you might think, well, that's obvious. Everybody knows things are made of atoms. But do you really understand what that means? Do you really feel it? Let's think about it together. Imagine you're holding a glass of water, just a simple glass of water. Now suppose we could magnify that water, make it bigger and bigger and bigger. At first you'd see, well, just smooth water, nothing special. Keep magnifying. Eventually you'd start to see tiny creatures swimming around, little paramecia, bacteria, all sorts of microscopic life. But that's not what we're after. Keep going. Magnify it more, 1 billion times. And now you see something extraordinary. The water isn't smooth anymore. It's made of little blobs, jiggling, wiggling, bouncing off each other. These are the atoms, well, actually molecules of water. Each one is 2 hydrogen atoms stuck to 1 oxygen atom, and they're all in perpetual motion. They never stop moving, never. And here's the thing that's so beautiful about this. Everything you see around you, everything you touch, everything you are, is made of these little jiggling things. The chair you're sitting on, the air you're breathing, your own body, all of it, just atoms, dancing around according to certain rules. Now, why don't the atoms just fly apart? Why does the chair stay a chair? Why doesn't the water just, I don't know, explode into the air? Well, it's because of this delicate balance. The atoms attract each other when they're a little distance apart. They want to come together. But if you try to squeeze them too close, they push back, hard, very hard. It's like, imagine you have 2 magnets. When they're far apart, they pull toward each other. But if you try to push them together the wrong way, they fight you. Atoms are something like that, except, well, the rules are different and much more complicated, but you get the idea. This balance, this push and pull, is what makes matter possible. It's what makes you possible. And the temperature is just a measure of how fast these atoms are jiggling. When you heat something up, you're making the atoms move faster. When you cool it down, they slow down. Think about ice, solid ice. You might think the atoms in ice are standing still, but they're not. They're vibrating in place, shaking back and forth around fixed positions, arranged in a beautiful crystalline pattern. They're stuck in a kind of cage made by their neighbors, but they're still moving. Now heat that ice up. What happens? The atoms start vibrating faster and faster until they shake so violently that they break free from their positions. The rigid structure falls apart, and now you have water, liquid water. The atoms are still connected, still attracted to each other, but now they can slide around, move past each other. That's why water flows. Keep heating it. The atoms move faster still, and eventually some of them are moving so fast that they just escape. They fly off into the air. That's evaporation. That's steam. You see, states of matter, solid, liquid, gas, they're not really different kinds of stuff. They're the same atoms, the same molecules, just moving at different speeds and arranged in different ways. And this is happening right now, everywhere, all the time. The air in this room is filled with molecules, nitrogen, oxygen, a little bit of other things, all bouncing around at hundreds of meters per second, crashing into each other, crashing into you. Right now, as you're listening to this, billions and billions of air molecules are hitting your skin every second. You don't feel them individually because each one is so tiny and there are so many of them coming from all directions. But collectively they create what we call air pressure. That's why the air pushes on things. It's just molecules banging into stuff. Isn't that wonderful? The whole world explained by these little dancing particles. But wait, there's more. Much more. Let's think about what holds atoms together in the first place. Why do atoms stick to each other to make molecules? Why do molecules stick together to make, well, everything? This is where it gets really interesting. You see, atoms aren't just little solid balls. They have structure. At the center of each atom is a tiny, dense nucleus made of protons and neutrons. And around that nucleus, there are electrons. Now, I won't pretend I can explain exactly what electrons are doing around the nucleus, because, honestly, they don't behave like anything you've ever seen. They're not little planets orbiting a sun. They're something stranger, much stranger. But we'll get to that. For now, what matters is this. Protons have a positive electrical charge. Electrons have a negative electrical charge. And opposite charges attract. So the electrons are attracted to the protons in the nucleus. That's what holds the atom together. But here's something remarkable. The electrical force, the force between charged particles, is incredibly strong, fantastically strong. It's about 1 billion, 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 billion times stronger than gravity. Think about that for a moment. When you pick up a ball, you're fighting against the gravity of the entire Earth, and you win, easily. That's because the electrical forces in your muscles, holding your atoms together, are so much stronger than gravity. Now, you might ask, if electrical forces are so strong, why don't we notice them all the time? Why aren't things flying around, attracted and repelled by electrical forces? The answer is balance. You see, there are two kinds of electrical charge, positive and negative. And most matter, most ordinary matter, has almost exactly equal amounts of positive and negative charge. The protons and electrons balance out. If you're standing next to someone, there are enormous electrical forces between all the atoms in your body and all the atoms in their body. Enormous. But the positive and negative charges are so perfectly balanced that they almost completely cancel out. The balance is incredibly precise. If you had just 1% more electrons than protons in your body, and the person next to you had 1% more electrons too, the repulsion between you would be enough to lift a weight equal to the entire Earth. That's how strong electrical forces are, and that's how precise the balance is. This balance, this near-perfect cancellation of positive and negative charges, is what makes ordinary life possible. Without it, matter couldn't exist as we know it. Everything would be pushed apart or pulled together by these tremendous forces. But sometimes the balance is a little off. And when that happens, you get chemistry. When atoms come close together, their electrons can interact. They can be shared between atoms. They can be traded. And this creates chemical bonds. This is how atoms stick together to form molecules. This is how molecules stick together to form, well, everything. The water in your glass. Each water molecule is made of one oxygen atom sharing electrons with two hydrogen atoms. The sharing isn't equal. Oxygen pulls the electrons a little more toward itself, so the water molecule has a slightly positive side and a slightly negative side. And that's why water molecules stick to each other. That's why water is wet. Let me tell you about something that amazed me when I first understood it. You know when you dissolve salt in water? Table salt, sodium chloride. What's happening there? Well, salt is made of sodium atoms and chlorine atoms, but they're not really neutral atoms anymore. The sodium has given up an electron to the chlorine, so you have positively charged sodium and negatively charged chlorine held together by electrical attraction. When you put salt in water, the water molecules, with their slightly positive and slightly negative ends, they crowd around the salt. The positive ends of the water molecules are attracted to the negative chlorine. The negative ends are attracted to the positive sodium. And gradually, the water molecules pull the salt apart. They separate the sodium from the chlorine and carry them away into the solution. That's dissolving. It's not magic. It's just atoms interacting according to their electrical properties. And burning is another beautiful example. When you burn wood or coal or anything, what's happening? The atoms in the fuel are rearranging themselves. They're finding new partners to stick to. The carbon in the wood combines with oxygen from the air to make carbon dioxide. The hydrogen combines with oxygen to make water. And these new combinations, these new molecules, are at a lower energy than the original ones. The extra energy has to go somewhere. It comes out as heat and light. That's fire. That's the warmth you feel from a burning log. It's atoms rearranging and energy being released. Now, here's something to think about. All of this, all of chemistry, all of biology, all of life itself, it's all just atoms following rules. Electrical forces, attractions and repulsions, that's it. The proteins in your body, made of atoms. The DNA that carries your genetic code, made of atoms. The neurons in your brain that are processing these words right now, made of atoms. And somehow, from these simple rules, from atoms jiggling and bouncing and sticking and unsticking, life emerges, consciousness emerges, you emerge. How does that happen? Honestly, we don't fully understand. It's one of the great mysteries, but we know it's atoms all the way down. Let's talk about something else now. Let's talk about the air around us. Air seems like nothing, doesn't it? You can't see it. You can barely feel it unless the wind is blowing. But air is very much something. It's a gas. And a gas is just a collection of atoms or molecules that are moving so fast and are so far apart that they don't stick together anymore. In a solid, the atoms are packed close together in fixed positions. In a liquid, they're still close together but can move around. In a gas, they're far apart and moving fast. The air in this room is mostly nitrogen molecules. Each one is 2 nitrogen atoms stuck together. About 20% is oxygen molecules, which we need to breathe. And there are tiny amounts of other things: argon, carbon dioxide, water vapor. These molecules are zooming around at tremendous speeds, hundreds of meters per second, faster than sound. They travel in straight lines until they hit something, another molecule, or a wall, or your skin, and then they bounce off in a new direction. The average distance a molecule travels before hitting another one is very small, much less than a millimeter. So even though they're moving incredibly fast, they don't get very far before changing direction. It's like trying to walk through a crowded room. You might be able to walk fast, but you keep bumping into people. And here's something interesting. The pressure of the air, the force it exerts on things, comes from all these molecular collisions. Each molecule that bounces off your skin gives you a tiny push. Individually, it's nothing. But there are so many molecules hitting you, millions of billions every second, that it adds up to a substantial force. At sea level, the air is pushing on you with a force of about 1 kilogram per square centimeter. That's a lot. Why doesn't it crush you? Because the air inside you is pushing back with the same force. The pressures balance out. When you go up a mountain, there's less air above you, so the pressure is lower. Your ears pop as the air inside them adjusts to the new pressure. Airplanes have to be pressurized so you can breathe normally at high altitudes. So, the atmosphere, it's not nothing. It's a sea of molecules, and we live at the bottom of that sea, adapted to its pressure and composition. Fish probably don't think much about the water they swim in, and we don't think much about the air we breathe. But it's there, it's real, it's made of atoms, everything is.
Now, I want to tell you about something strange, something beautiful, something that will maybe change the way you think about the world.
It has to do with gravity, and with space, and with time. You know about gravity, right? Newton figured it out. Every object in the universe attracts every other object with a force that depends on their masses and the distance between them. The more massive the objects, the stronger the force. The farther apart they are, the weaker the force. This simple rule, it explains so much. Why things fall down, why the moon orbits the Earth, why the Earth orbits the sun, why galaxies hold together. One simple rule, and it describes the motion of everything from an apple to a galaxy. Newton's law of gravity is amazingly successful. We used it to send men to the moon. We use it every day to predict the motions of planets and satellites. But Newton's law has a problem, a conceptual problem. Newton himself was bothered by it. He said, how can one object affect another object that's far away? There's nothing between them. How does the sun reach out and pull on the Earth across 90 million miles of empty space? It seems like magic. Newton didn't have an answer. He just said, this is how it works. The math describes it. But I don't know the mechanism. It took Einstein to figure it out. And his answer, it's so strange, so beautiful, that it changed our understanding of reality itself. Einstein said, gravity isn't a force at all. Not really. It's a curvature of space and time. What does that mean? Let me try to explain. Imagine you're a bug living on a flat surface, a perfectly flat plane. You can crawl around, you can draw lines, you can measure distances. To you, your world is flat. It obeys the rules of flat geometry. Now imagine a different bug living on the surface of a sphere. To this bug, well, his world looks flat too, if he only looks at small areas. But if he measures carefully, if he draws big triangles and measures the angles, he'll find something strange. The angles of his triangle don't add up to the same as they would on a flat surface. His geometry is different. The bug can't see that his surface is curved. He lives on it. He can only measure within it. But by making careful measurements, he can figure out that his space is not flat. Einstein said, our universe is like that. Space itself can be curved, and it's curved by the presence of mass and energy. Near a massive object like the sun, space is curved, and when things move through curved space, they follow curved paths. Not because a force is pushing them, but because a straight line through curved space is itself curved. Imagine rolling a ball across a trampoline. If the trampoline is flat, the ball goes straight. But if there's a heavy bowling ball sitting on the trampoline making a dip, then a ball rolling past will curve toward the dip. It looks like the bowling ball is attracting the other ball, but really the other ball is just following the curved surface. That's a rough analogy for what gravity is. Mass curves space, and objects move along the curves. But it's not just space that's curved. Time is too. This is the really strange part. Time runs at different rates depending on where you are in a gravitational field. Near a massive object, time runs slower. A clock at the top of a mountain runs slightly faster than a clock at sea level. Not because there's anything wrong with the clocks, but because time itself is flowing at different rates. The difference is tiny, incredibly tiny. You wouldn't notice it in everyday life, but it's real. It's been measured. And if you're going to navigate very precisely, like certain kinds of scientific instruments do, you have to take it into account. Space and time are not separate things. They're woven together into something called spacetime. And spacetime is curved by matter and energy. And objects move through spacetime along the straightest possible paths, which look curved to us because space-time itself is curved. That's Einstein's theory of gravity, general relativity. It gives slightly different predictions than Newton's theory, very slightly different in most cases, but in extreme situations, near very massive objects or at very high speeds, the differences become significant.
Einstein's theory predicted that light would be bent by gravity, that even light with no mass would follow the curves in space-time. And that prediction was tested in 1919 during a solar eclipse, and it was confirmed. Light from distant stars was bent as it passed near the sun. Einstein's theory also predicted that time would run differently at different heights in a gravitational field, and that's been confirmed too. Every time Einstein's predictions have been tested, nature has chosen Einstein. So the universe we live in, it's not a fixed stage where events play out. Space and time themselves are dynamic. They curve and stretch and respond to the matter within them, and matter responds to the curves. Everything affects everything else. Everything is connected. That's a beautiful thing, isn't it? Now, where were we? Ah, yes. We were talking about how space and time are curved by matter. How gravity isn't really a force pulling things together, but rather the shape of space-time itself guiding things along. But let me step back for a moment. Let me tell you about something even more fundamental, something that underlies everything we've talked about so far, the laws of nature. What is a law of nature? It's not like a law passed by a government. You can break those laws. You might get punished, but you can break them. A law of nature is different. You can't break it. It's not a rule that nature follows. It's a description of what nature does, always, everywhere, without exception. And here's the remarkable thing. The laws of nature are universal. The same rules that govern how atoms behave here on Earth, they work the same way on the moon, on Mars, in distant galaxies. Everywhere we've looked, everywhere we've tested, the laws are the same. Think about what that means. A star 1 billion light years away, so far that the light we see from it left before there was life on Earth. That star is made of the same atoms, following the same rules as the stuff in your body right now. We know this because we can analyze the light from distant stars. Different atoms absorb and emit light at specific frequencies, like fingerprints, and we see the same fingerprints in starlight that we see in our laboratories here on Earth. Hydrogen is hydrogen, whether it's here or across the universe. This universality, it's not something we had to assume, it's something we discovered. We looked and we measured, and we found that nature is consistent, the same everywhere, the same always. Well, almost always. We think the laws have been the same throughout time, but honestly, we can only check so far back. There might have been different rules at the very beginning, in the first moments after the Big Bang. We don't know. But as far as we can tell, since those very early times, the rules have been constant. And this is what makes science possible. If the rules changed from place to place or from day to day, we couldn't figure anything out. But because nature is consistent, we can learn its rules. We can discover them in our laboratories and then apply them to understand distant stars and ancient light and the whole vast universe. Now let me tell you something that I find absolutely fascinating. The laws of physics, they have a property called symmetry. What do I mean by symmetry? Well, you know how a circle looks the same no matter how you rotate it? That's a symmetry. The circle is unchanged by rotation. The laws of physics have symmetries like that. They're unchanged by certain transformations. For example, the laws of physics are the same everywhere in space. If you do an experiment here and then move your equipment 100 miles away and do the same experiment, you get the same result. The laws don't care about where you are. That's a symmetry. The laws are unchanged by translation in space. Similarly, the laws are the same at all times. An experiment done today gives the same result as the same experiment done yesterday or 100 years ago. The laws are unchanged by translation in time. And the laws are the same in all directions. It doesn't matter which way you're facing. Physics works the same way pointing north as it does pointing east. The laws are unchanged by rotation.
Now here's the beautiful part. These symmetries aren't just aesthetic properties. They have consequences, deep consequences. There's a theorem discovered by a mathematician named Emmy Noether that connects symmetries to conservation laws. If the laws of physics are the same everywhere in space, that implies conservation of momentum. If you have a bunch of particles interacting, their total momentum stays constant. Momentum is conserved. If the laws are the same at all times, that implies conservation of energy. Energy can change form, kinetic to potential to thermal and so on, but the total amount stays the same. Energy is conserved. If the laws are the same in all directions, that implies conservation of angular momentum. Spinning things keep spinning. Isn't that remarkable? The symmetries of nature's laws automatically give you these conservation principles that we use every day in physics. It's all connected. So, when you see a planet orbiting a star, maintaining its angular momentum year after year, that's not some separate rule. That's a consequence of the fact that the laws of physics don't prefer any particular direction. The symmetry of the laws shows up as conservation of angular momentum. When a ball rolls down a hill and speeds up, trading potential energy for kinetic energy, but the total energy stays the same, that's a consequence of the laws being the same at all time. The conservation laws aren't additional rules tacked onto physics. They emerge from the symmetries. They're built into the structure of reality itself. Now, I should tell you, nature isn't perfectly symmetrical in every way. There are some symmetries that we thought existed but turned out to be broken. For a long time, physicists believed that nature had mirror symmetry. They thought if you could somehow flip the universe left to right, like looking at it in a mirror, all the laws would still work the same way. Makes sense, right? Why would nature care about left versus right? But it turns out nature does care, a little bit, in certain rare circumstances. There are some nuclear reactions involving what we call the weak force, where left and right are treated differently. If you looked at these reactions in a mirror, you'd see something that doesn't happen in the real world, or happens with different probability. This was a shock when it was discovered in the 1950s. It seemed so strange. Why would nature distinguish between left and right? And then it got stranger still. Physicists thought, okay, maybe nature isn't symmetric under mirror reflection alone, but maybe if you also swap matter for antimatter, maybe then it's symmetric. Antimatter, that's stuff made of particles with opposite charges. An anti-electron, called a positron, has positive charge instead of negative. An antiproton has negative charge instead of positive. An atom made of antimatter would have an antiproton nucleus with a positron orbiting it. Now, anti-electrons and antiprotons are real. We make them all the time in particle accelerators, and we can make antihydrogen atoms. They behave almost exactly like regular hydrogen, except the charges are flipped. So physicists thought, if you take a reaction, flip it in a mirror, and swap all the matter for antimatter, then it should look the same as the original. But no, even that symmetry is broken, slightly, in some very rare reactions. This is deeply puzzling, and also it might be the reason you exist. Here's the thing. In the early universe, right after the Big Bang, matter and antimatter were created in vast quantities. They should have been created in equal amounts. And when matter and antimatter meet, they annihilate each other. Poof, gone, converted to pure energy. If there had been exactly equal amounts of matter and antimatter, they would have completely annihilated, and the universe would be filled with radiation, but no atoms, no stars, no planets, no people. But we're here. The universe is made of matter, which means somehow there was a tiny imbalance, a little bit more matter than antimatter. The antimatter all annihilated with an equal amount of matter, and the leftover matter is what we're made of. That tiny imbalance, it might be connected to the breaking of these symmetries. The details are still being worked out, but somehow the slight asymmetry in nature's laws led to a universe where matter could exist.
Let me talk about something else now. Something that seems completely different, but is actually connected to everything. Light. What is light? This question has puzzled people for centuries. Newton thought light was made of tiny particles, corpuscles, he called them. Then experiments showed that light behaves like a wave. It diffracts, it interferes, it does all the things waves do. So for a long time, physicists believed light was definitely a wave, an electromagnetic wave, oscillating electric and magnetic fields traveling through space. And then came quantum mechanics, and everything got strange. Let's talk about what happens when you shoot light at a screen with two thin slits in it. This is called the double slit experiment, and it's one of the most important experiments in physics. If light is a wave, what happens? The wave passes through both slits. The waves coming from the two slits spread out and overlap. In some places, the peaks of the waves line up, and you get a bright spot. In other places, the peak of one wave meets the trough of the other, and they cancel out. You get a dark spot. The result is a pattern of bright and dark stripes on a screen behind the slits, an interference pattern. This is exactly what you see if you do the experiment with water waves, and it's what you see with light, too. So light is a wave. Case closed, right? But wait, what happens if you turn the light down really, really low? So low that you're sending just one photon at a time. A photon, that's the smallest unit of light, the quantum of light. Einstein figured out that light comes in these discrete packets, each carrying a specific amount of energy. So you send one photon at a time toward the two slits. Where does it go? Well, if it's a particle, it should go through one slit or the other, right? A particle has to take some definite path. And indeed, when the photon hits the screen, it hits at a definite point. You see a single spot. One photon, one spot. That sure looks like a particle. But here's the thing. If you keep sending photons one at a time and record where each one lands and build up a picture over many, many photons, what pattern do you get? You get the interference pattern. Each individual photon hits at one spot like a particle. But over many photons, they form the same pattern you'd expect from a wave going through both slits at once. How is that possible? How can a single photon going through one slit or the other know about the other slit? How can it know where the bright and dark spots should be? The only way to explain it, the photon somehow goes through both slits at once. It interferes with itself. But that doesn't make any sense either. How can one particle go through two slits? This is quantum mechanics, and it doesn't make sense in terms of our everyday experience. It doesn't behave like anything you've ever seen. The honest answer is, we don't know what the photon is really doing. We can't know, because if we try to find out which slit it went through, if we try to catch it in the act, the interference pattern disappears. Let me say that again, because it's so strange. If you set up a detector to see which slit the photon goes through, the photon behaves like a particle. It goes through one slit or the other, and you don't get the interference pattern. If you don't look, if you don't try to find out which path it took, then it goes through both, and you get interference. The act of looking changes what happens. This isn't the defect in our instruments. It's not that we're disturbing the photon with our clumsy measurements. It's more fundamental than that. The photon doesn't have a definite path until you measure it. Before measurement, it's in a superposition of going through both slits. It's not that we don't know which slit it went through. It genuinely went through both, or neither. The question doesn't have a definite answer until you ask it. This is the heart of quantum mechanics, and it applies not just to photons, but to everything. Electrons, atoms, everything.
Now, let me tell you something even stranger. This same experiment works with electrons, and with atoms, and with molecules. Anything small enough that quantum effects matter. Electrons are definitely particles. They have mass, they have charge. When they hit a screen, they leave a dot, particle behavior. But send them through two slits, and they make an interference pattern, wave behavior. An electron, a chunk of matter, going through both slits at once, interfering with itself. So which is it? Is an electron a wave or a particle? Neither. It's something else. Something that has no analogy in the world we can see and touch. Something that shows wave properties in some experiments and particle properties in others. We call it wave-particle duality. But that's just a name. We haven't really explained anything by giving it a name. The universe, at its most fundamental level, doesn't operate by the rules of common sense. It operates by rules that are deeply counterintuitive, rules that we've only discovered because we looked, we measured, we did experiments, and the experiments told us this is how it is. Accept it. There's a principle in quantum mechanics called the uncertainty principle. It was discovered by Heisenberg, and it says something very strange about what we can know. It says you cannot know both the position and the momentum of a particle with perfect precision. The more precisely you know one, the less precisely you can know the other. This isn't because our instruments are bad, it's fundamental. The universe itself doesn't have definite values for both quantities at the same time. Think about what that means. In classical physics, we imagined that particles had definite positions and definite velocities at every moment. We just had to measure carefully enough to find out what they were. Quantum mechanics says no. That picture is wrong. A particle doesn't have a definite position and a definite momentum at the same time. It can't. The universe won't allow it. You might ask, well, what is the particle doing when we're not measuring it? That's a question that quantum mechanics doesn't really answer. Different physicists have different interpretations. Some say the particle is in a superposition of all possible states. Some say there are many parallel worlds where every possibility happens. Some say we shouldn't ask what's really happening because the only thing we can know is what we measure. I don't know the answer. Nobody does. But what we do know is how to calculate. We know the rules. We know how to predict the probabilities of different outcomes. And those predictions are spectacularly successful. Every piece of technology that uses quantum mechanics, lasers, transistors, electronics, all of it works because we understand the rules, even if we don't fully understand what they mean. Let me bring this back to atoms. Remember atoms? That's where we started. Why do atoms exist at all? Why doesn't the electron just fall into the nucleus? Classically, it should. The electron is negatively charged, the proton is positively charged, they attract. The electron should spiral in and collapse onto the proton. But quantum mechanics saves the atom. The uncertainty principle saves it. Here's why. If the electron were confined to a tiny space near the nucleus, we would know its position very precisely. But then, by the uncertainty principle, its momentum would be very uncertain. It would have to be moving around rapidly. And that rapid motion gives the electron kinetic energy. The more you try to confine it, the more kinetic energy it has. So there's a balance. The electrical attraction pulls the electron toward the nucleus, but the uncertainty principle gives it energy that resists the confinement. The electron settles into an equilibrium, not too close, not too far, where these effects balance out. That's why atoms have the size they do. It's quantum mechanics. Without it, atoms couldn't exist. Matter couldn't exist. You couldn't exist.
Now, I want to tell you about something strange, something beautiful, something that will maybe change the way you think about the world. It has to do with gravity and with space and with time. You know about gravity, right? Newton figured it out. Every object in the universe attracts every other object with a force that depends on their masses and the distance between them. The more massive the objects, the stronger the force. The farther apart they are, the weaker the force. This simple rule, it explains so much. Why things fall down, why the moon orbits the Earth, why the Earth orbits the sun, why galaxies hold together. One simple rule, and it describes the motion of everything from an apple to a galaxy. Newton's law of gravity is amazingly successful. We used it to send men to the moon. We use it every day to predict the motions of planets and satellites. But Newton's law has a problem, a conceptual problem. Newton himself was bothered by it. He said, how can one object affect another object that's far away? There's nothing between them. How does the sun reach out and pull on the Earth across 90 million miles of empty space? It seems like magic. Newton didn't have an answer. He just said, this is how it works. The math describes it. But I don't know the mechanism. It took Einstein to figure it out. And his answer, it's so strange, so beautiful, that it changed our understanding of reality itself. Einstein said, gravity isn't a force at all. Not really. It's a curvature of space and time. What does that mean? Let me try to explain. Imagine you're a bug living on a flat surface, a perfectly flat plane. You can crawl around, you can draw lines, you can measure distances. To you, your world is flat. It obeys the rules of flat geometry. Now imagine a different bug living on the surface of a sphere. To this bug, well, his world looks flat too, if he only looks at small areas. But if he measures carefully, if he draws big triangles and measures the angles, he'll find something strange. The angles of his triangle don't add up to the same as they would on a flat surface. His geometry is different. The bug can't see that his surface is curved. He lives on it. He can only measure within it. But by making careful measurements, he can figure out that his space is not flat. Einstein said, our universe is like that. Space itself can be curved, and it's curved by the presence of mass and energy. Near a massive object like the sun, space is curved. And when things move through curved space, they follow curved paths.
not because a force is pushing them, but because a straight line through curved space is itself curved. Imagine rolling a ball across a trampoline. If the trampoline is flat, the ball goes straight. But if there's a heavy bowling ball sitting on the trampoline, making a dip, then a ball rolling past will curve toward the dip. It looks like the bowling ball is attracting the other ball, but really the other ball is just following the curved surface. That's a rough analogy for what gravity is. Mass curves space, and objects move along the curves. But it's not just space that's curved, time is too. This is the really strange part. Time runs at different rates depending on where you are in a gravitational field. Near a massive object, time runs slower. A clock at the top of a mountain runs slightly faster than a clock at sea level. Not because there's anything wrong with the clocks, but because time itself is flowing at different rates. The difference is tiny, incredibly tiny. You wouldn't notice it in everyday life, but it's real. It's been measured. And if you're going to navigate very precisely, like certain kinds of scientific instruments do, you have to take it into account. Space and time are not separate things. They're woven together into something called space-time. And space-time is curved by matter and energy. And objects move through space-time along the straightest possible paths, which look curved to us because space-time itself is curved. That's Einstein's theory of gravity, general relativity. It gives slightly different predictions than Newton's theory, very slightly different in most cases, but in extreme situations, near very massive objects or at very high speeds, the differences become significant.
The whole universe depends on quantum mechanics, not in some abstract philosophical sense. Practically, atoms are stable because of it. Chemistry works because of it. Stars shine because of it. Inside the sun, hydrogen is being converted to helium. Protons are fusing together, releasing energy. This is what powers the sun, what powers all stars. But for protons to fuse, they have to get close enough for the nuclear force to grab them. And there's a problem. Protons are positively charged. They repel each other. The electrical repulsion keeps them apart. Classically, the protons in the sun aren't hot enough, they're not moving fast enough, to overcome this repulsion and get close enough to fuse. But quantum mechanics lets them cheat. There's a phenomenon called quantum tunneling. A particle can tunnel through a barrier that it doesn't have enough energy to climb over. Imagine a ball rolling toward a hill. Classically, if the ball doesn't have enough energy to get over the hill, it rolls back. It can't pass. But a quantum particle, it has a chance of appearing on the other side of the hill. Not going over, not going around, just appearing there. The probability might be tiny, but it's not zero. In the sun, protons tunnel through the electrical barrier and fuse together. The probability for any one pair of protons is extremely small. But there are so many protons in the sun, so many collisions every second, that fusion happens often enough to power the sun for billions of years. Quantum tunneling is why the sun shines, why we're here, why there's warmth and light and life. You see how it all connects? Atoms, quantum mechanics, the stability of matter, the burning of stars. It's all one story, one set of rules playing out on different scales. And the rules are strange, deeply strange. They don't match our intuitions. They don't match common sense, but they work. They describe reality as we find it. Nature doesn't care about our intuitions. Nature does what it does. And our job as curious beings is to figure out what that is. Now, let me talk about forces. We've mentioned gravity, we've mentioned electrical forces, but what are forces really? In the modern view, forces aren't what they seem. They're not pushes and pulls acting across empty space. They're something more subtle, something to do with fields and particles and exchanges. Let's start with the electromagnetic force, the force between charged particles. In quantum mechanics, this force arises from the exchange of photons, particles of light. Here's the picture. Two electrons approach each other.
They repel, right? They're both negative, so they push apart. But how does that repulsion happen? The electrons exchange photons. One electron emits a photon, the other absorbs it. And the exchange of this photon somehow transfers momentum, pushing the electrons apart. This sounds very strange, and I won't pretend I can explain it in simple terms, but the mathematics works out. When you calculate the effects of all these photon exchanges, you get exactly the electromagnetic force that we observe. The photons being exchanged here aren't real photons that you could detect. They're called virtual photons. They exist only during the interaction, and they violate the normal rules that real photons follow. But their effects are real. All the forces we know, except maybe gravity, work this way. Forces arise from the exchange of particles. The electromagnetic force comes from exchanging photons. The strong nuclear force, which holds protons and neutrons together in nuclei, comes from exchanging particles called gluons. The weak nuclear force, responsible for certain kinds of radioactive decay, comes from exchanging particles called W and Z bosons. And gravity? Well, if the pattern holds, gravity should come from exchanging particles called gravitons. But we've never detected a graviton. And our quantum theory of gravity is incomplete. It doesn't work properly yet.
Gravity is the odd one out. The other forces fit beautifully into the quantum framework.
Gravity is stubborn. It doesn't want to cooperate. Figuring out how to combine gravity with quantum mechanics is one of the great unsolved problems in physics. Some of the smartest people in the world have been working on it for decades. String theory is one attempt. There are others. We don't have the answer yet. But someday we might. And when we do, we'll have a theory of everything. A single framework that describes all of nature's forces, all of nature's particles, everything. Wouldn't that be something? A complete theory of physics, written on a single page maybe. All the rules of the universe, all the laws that govern everything from atoms to galaxies, all of it captured in one beautiful framework. Is that possible? We don't know. Maybe the universe is like that. Maybe there's a simple underlying theory. Or maybe it's more complicated. Maybe there are layers we haven't discovered yet. We won't know until we look, until we build new experiments, until we test new ideas. That's the adventure of science. That's what makes it exciting. We don't know what we'll find, but we keep looking. Let me tell you about something wonderful, something that gives me hope about human beings and our ability to understand the universe. The laws of physics are mathematical. They're written in the language of mathematics. And that mathematics is beautiful, not just useful, beautiful. The equations have symmetry, they have elegance, they have a kind of inevitability about them, as if they couldn't be any other way. Why should that be? Why should the deep laws of nature be expressible in beautiful mathematics? Why should the universe be comprehensible at all? I don't know. Nobody knows. But it's true. The universe is comprehensible. We can understand it. Not completely, not yet, but we've made astonishing progress. From a few simple principles, we can derive the motions of planets, the behavior of light, the structure of atoms, the evolution of stars. We can understand things that happen on the other side of the universe, billions of years ago. Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible. I think about that a lot. Here we are, apes on a small planet, evolved to find food and avoid predators. And somehow we figured out quantum mechanics, general relativity, the expansion of the universe, the age of the cosmos. Our brains weren't designed for this. Evolution didn't optimize us for understanding physics, and yet we can do it. That's remarkable. That's worth celebrating.
Now, let me tell you about something that I think is one of the most beautiful ideas in all of physics. It's called the principle of least action. When I was in high school, my physics teacher, his name was Mr. Beta, he called me down one day after class and said, "You look bored. I want to tell you something interesting." And then he told me something that I found absolutely fascinating. I've been thinking about it ever since. Every time the subject comes up, I work on it. I can't leave it alone. Here's what he told me.
Suppose you throw a ball up in the air. It goes up, slows down, stops for an instant, then comes back down. A simple parabola. We all know what happens. Now, Newton would explain this using forces. The ball has gravity pulling it down. That force causes an acceleration. You can calculate the path step by step. At each moment, figure out the force, figure out how the velocity changes, figure out where the ball goes next. That works. It gives you the right answer. But there's another way to think about it, a completely different way, and it's kind of magical. Instead of thinking about forces pushing the ball around moment by moment, think about the whole path at once. The ball starts here, ends there, takes a certain amount of time. There are infinitely many paths it could take between start and finish. It could go straight up and straight down. It could wiggle around. It could go way up high and come back. It could barely leave your hand. Among all these possible paths, the ball takes one particular path, the real path, the parabola. Why that path? What's special about it? Here's the amazing thing. You can calculate a number for each possible path. This number is called the action, and the path that nature actually takes is the one for which the action is smallest, or more precisely, it's the path for which the action is stationary. It's at a minimum, or sometimes a maximum, or a saddle point, but in most cases, it's a minimum, the path of least action. So nature, somehow, considers all possible paths, calculates this number for each one, and picks the path with the smallest action. How do you calculate the action? You take the kinetic energy of the ball at each moment, subtract the potential energy, and add all that up over the whole path, integrated over time, as we say. Kinetic energy minus potential energy, integrated over time. That's the action. And the real path, the path that obeys Newton's laws, is the one that makes this integral as small as possible. Now you might say, so what? It's just another way of getting the same answer. Newton's way works fine. Why bother with this? But here's the thing. This principle, the principle of least action, it's not just another way of doing the same calculation. It reveals something deep about nature. It tells us that nature is economical, efficient. Among all the ways things could happen, nature picks the way that minimizes something. There's an optimization going on. And the really remarkable thing is that this principle is universal. It doesn't just work for balls flying through the air, it works for everything. Planets orbiting stars, light traveling through glass, electrons in atoms, everything. When you first hear it, it sounds almost mystical, like nature is planning ahead, like the ball knows where it's going to end up and chooses the optimal path to get there. But that's not really what's happening. There's no planning, no foresight. The principle of least action is just another way of expressing the same laws of physics. It's mathematically equivalent to Newton's laws, but it's a different way of looking at things. And sometimes a different perspective reveals new insights. Let me give you an example. Light. You know that light travels in straight lines, right? In empty space, anyway. A beam of light goes from here to there along the shortest path. But what happens when light goes from air into water or through a lens? It bends. It refracts. Why does it bend? Well, you could explain it with waves and wave fronts and all that. But there's another explanation. One that uses the principle of least action, or in this case, a related principle called Fermat's principle. Fermat's principle says that light takes the path of least time, not least distance, least time. In empty space, the path of least time is also the path of least distance, a straight line. Light goes straight, but light travels at different speeds in different materials. It's slower in water than in air, slower in glass than in water.
So if light is going from a point in air to a point in water, the path of least time isn't the straight line. If it goes straight, it spends more time in the slow medium, the water. Instead, light bends. It takes a path that spends less time in the water and more time in the air. The total time is minimized. And when you work out the math, the angle of bending, you get exactly Snell's law of refraction, the law that describes how light bends when it enters a new medium. Isn't that beautiful? Light doesn't know about Snell's law. Light doesn't do calculations, but it behaves as if it's finding the fastest path between 2 points. How does it do that? How does light know which path is fastest without trying all of them? This is where quantum mechanics comes in. And the answer is, it does try all of them. In quantum mechanics, light doesn't take just one path, it takes all paths. Every possible path from here to there, light explores them all. But the paths interfere with each other. Remember interference? Waves adding up or canceling out. Most paths cancel each other out. A path that's a little different from a neighboring path will have a different phase, and they'll tend to cancel. But near the path of least time, something special happened. Neighboring paths have almost the same action, almost the same phase. They add up instead of canceling. They reinforce each other. So the light ends up going along the path of least time, not because it chose that path, but because all the other paths canceled out. This is Feynman's path integral formulation of quantum mechanics. Well, I suppose I should be modest about it since, anyway, the idea is that particles explore all possible paths and the paths interfere, and the classical path, the path of least action, emerges from this interference. It's a beautiful unification. Classical physics, where things take definite paths, emerges from quantum physics, where things explore all paths, but most of them cancel out. Now let me tell you about something else, something about symmetry and conservation laws, and how they're all connected to this principle of least action. Remember I mentioned Emmy Noether, the mathematician who discovered the connection between symmetries and conservation laws? Her theorem works through the principle of least action. The action has certain symmetries. It doesn't change under certain transformations, and those symmetries automatically imply conservation laws. If the action doesn't change when you shift everything in space, you get conservation of momentum. If the action doesn't change when you shift everything in time, you get conservation of energy. If the action doesn't change when you rotate everything, you get conservation of angular momentum. It's all connected. The principle of least action, the symmetries of nature, the conservation laws, they're not separate ideas. They're different facets of the same underlying structure. This is what makes physics beautiful. Not just that we can predict what will happen, but that the predictions come from deep principles, principles with elegance and inevitability. When you see how it all fits together, you get a feeling that this is how it has to be, that nature couldn't be any other way. Maybe that feeling is wrong. Maybe nature could be completely different, but the feeling is there, and it's part of what drives physicists to keep looking deeper. Let me now talk about something vast, the universe itself. We've been talking about atoms and particles and forces, small things, but the same laws that govern the small also govern the large. The same physics that explains an electron also explains a galaxy. So what do we know about the universe as a whole? First, the universe is big, unimaginably big. The nearest star to our sun is about 4 light years away. That means light, traveling at 300,000 kilometers per second, takes 4 years to get there. Our galaxy, the Milky Way, contains hundreds of billions of stars. It's about 100,000 light years across. And there are hundreds of billions of galaxies in the observable universe, each one containing billions of stars. The observable universe is about 90 billion light years across. And that's just the part we can see. There might be more beyond that, beyond the reach of light that has had time to reach us. So, how do we know all this? We can't travel to distant galaxies. We can't even travel to nearby stars. All we can do is look. We collect the light that reaches us, and we analyze it. And from that light, we've learned astonishing things. The universe is expanding. The galaxies are moving apart from each other.
The farther away a galaxy is, the faster it's receding. This was discovered in the 1920s by Edwin Hubble. He measured the distances to galaxies and their speeds, and he found this relationship. Distant galaxies are moving away from us faster than nearby ones. Now you might think, are we at the center of the universe? Is everything moving away from us specifically? No, it's not like that. The expansion is happening everywhere. No matter where you are in the universe, you'd see the same thing. Galaxies moving away from you, with more distant ones moving faster. It's like, imagine dots on a balloon. As you inflate the balloon, all the dots move apart from each other. From the perspective of any one dot, all the others are receding. There's no center. The expansion is happening everywhere. Space itself is expanding. The galaxies aren't moving through space. Space is stretching, carrying the galaxies along with it. If the universe is expanding now, what about the past? If we run the movie backward, the galaxies get closer together. Space contracts. Everything gets denser and hotter. Go back far enough, and the entire universe was compressed into an incredibly dense, incredibly hot state. And then it started expanding, rapidly, explosively. This is the Big Bang, the beginning of our universe, or at least the beginning of the universe as we know it. The Big Bang wasn't an explosion in space, it was an explosion of space. Space itself came into being and started expanding. What was before the Big Bang? Honestly, we don't know. Our physics breaks down at that moment. The equations give infinities and nonsense. We don't have a theory that can describe what happened at time zero. Maybe time itself began with the Big Bang. Maybe asking what was before doesn't make sense. Like asking what's north of the North Pole. Or maybe there was something before. Some other state. Some other universe. We don't know. But we do know what happened shortly after the Big Bang. The universe was hot. Unbelievably hot. So hot that atoms couldn't exist. Matter was a soup of particles. Protons, neutrons, electrons, all flying around at tremendous speeds, colliding, interacting. As the universe expanded, it cooled, like a gas expanding and cooling. And as it cooled, particles could start to combine. About 3 minutes after the Big Bang, protons and neutrons came together to form the nuclei of light elements, hydrogen, helium, a little bit of lithium. This is called nucleosynthesis. But heavier elements, carbon, oxygen, iron, they weren't made in the Big Bang. The universe cooled too fast. There wasn't time. Where did the heavy elements come from? From stars. Inside stars, nuclear fusion builds heavier elements from lighter ones. Hydrogen fuses to helium. Helium fuses to carbon. Carbon to oxygen, and so on up the periodic table. When massive stars die, they explode, supernovae, and in those explosions, even heavier elements are created and scattered into space. The carbon in your body was made inside a star. The oxygen you breathe, the iron in your blood, all of it was forged in the hearts of stars that exploded billions of years ago. You are made of star stuff, literally. After the Big Bang, the universe was filled with a hot plasma. Light couldn't travel far. It kept scattering off the charged particles. The universe was opaque. But about 400,000 years later, the universe had cooled enough for electrons to combine with nuclei to form neutral atoms. And suddenly, light could travel freely. The universe became transparent. The light from that moment is still traveling through space. It's been stretched by the expansion of the universe, so it's no longer visible light. It's microwaves now. We call it the cosmic microwave background radiation.
We can detect it with radio telescopes. It's coming from every direction in the sky. It's the oldest light in the universe. A snapshot of what the universe looked like 400,000 years after the Big Bang. And here's the amazing thing. The cosmic microwave background is almost perfectly uniform. The same temperature in every direction.
to about 1 part in 100,000. But there are tiny variations, tiny differences in temperature from one spot to another. And those tiny differences, they're the seeds of everything we see today. The slightly denser regions had slightly stronger gravity. They attracted more matter. Over billions of years, they grew. They collapsed into galaxies and clusters of galaxies. The giant structures we see in the universe today, the cosmic web of galaxies and voids, they grew from those tiny fluctuations in the early universe. Where did the fluctuations come from? This is where it gets really speculative. The leading theory is that they came from quantum mechanics. In the very early universe, when it was unimaginably small, quantum fluctuations, those random uncertainties we talked about earlier, they left an imprint on the fabric of space itself. And then the universe expanded rapidly, stretching those tiny quantum fluctuations into the large-scale variations we see in the cosmic microwave background. Quantum mechanics determining the structure of the universe, the very small shaping the very large. Let me tell you about something mysterious, something we don't understand at all. When we look at galaxies, we can measure how fast they're rotating. Stars in the outer parts of galaxies are orbiting around the center, and we can see how fast they're moving. If we calculate how much mass is needed to keep those stars in orbit, how much gravity is required, we get a number. Then we add up all the visible matter in the galaxy, the stars, the gas, the dust, and we get a different number. The visible matter isn't enough, not nearly enough. The stars are moving too fast for the gravity from the visible matter to hold them in orbit. Something else must be providing the extra gravity, something we can't see. We call it dark matter. Dark matter doesn't emit light. It doesn't absorb light. It doesn't interact with ordinary matter except through gravity. It's invisible, but its gravitational effects are everywhere. Galaxies are embedded in vast halos of dark matter. Galaxy clusters are held together by dark matter. The large-scale structure of the universe is shaped by dark matter, and there's a lot of it. About 5 times as much dark matter as ordinary matter in the universe. Most of the matter in the universe is stuff we can't see and don't understand. What is dark matter? We don't know. It's not ordinary atoms. It's not protons and neutrons and electrons. It's something else. Some new kind of particle, probably, but we haven't detected it directly. We only see its gravitational effects. And then there's something even stranger. Dark energy. When we measure the expansion of the universe very carefully, looking at distant supernovae, we find something unexpected. The expansion is accelerating. That's weird. Gravity should be slowing the expansion down. All the matter in the universe, pulling on all the other matter, should act like a brake, gradually slowing the expansion. But instead, it's speeding up. Something is pushing the universe apart, counteracting gravity, making the expansion accelerate. We call this dark energy, and we have no idea what it is. Dark energy makes up about 70% of the total energy in the universe. Dark matter is about 25%. Ordinary matter, the stuff we're made of, the stuff we can see, is only about 5%. So everything we know, all the atoms, all the stars, all the galaxies, that's just 5% of what's out there. The rest is dark, unknown, mysterious. We're profoundly ignorant about most of the universe. But you know, that's okay. That's exciting, actually. It means there's so much left to discover, so many mysteries to solve. If we knew everything, what would be the point? The fun is in the figuring out. Let me talk about time now. We've mentioned time a lot, but what is time really? In Newton's physics, time was absolute. It flowed at the same rate everywhere, for everyone. A universal clock ticking away, independent of anything else. Einstein showed that's wrong. Time is relative. It flows at different rates for different observers. A clock moving fast relative to you runs slow compared to your clock. A clock in a strong gravitational field runs slow compared to a clock far from gravity. We've measured these effects. They're real. They're not big in everyday life, but they're definitely there. So time is flexible, stretchable, part of the fabric of space-time that can be warped by mass and motion.
But there's another mystery about time. Why does it have a direction? The laws of physics at a fundamental level are mostly symmetric in time. If you film a simple interaction between particles and play it backward, the result still obeys the laws of physics. The laws don't distinguish between past and future. And yet, we experience a clear direction of time. The past is different from the future. We remember the past, but not the future. Eggs break, but don't unbreak. Ice melts, but, well, it can refreeze. But the overall tendency in the universe is for order to decrease, for things to become more disordered. This is the second law of thermodynamics. Entropy increases, disorder grows. But where does this arrow of time come from? If the fundamental laws are time symmetric, why is there a direction? The answer seems to be that the universe started in a very special, very low entropy state. The Big Bang was extremely ordered in some sense. And ever since, entropy has been increasing as the universe evolves toward more probable, more disordered states. The arrow of time points from the low entropy past toward the high entropy future. But this just pushes the question back. Why did the universe start in such a low entropy state? We don't know. It's one of the deepest mysteries in physics. You know, the more we learn, the more questions we uncover. Every answer reveals 10 new mysteries. Is that frustrating? Maybe, but I think it's wonderful. It means the adventure never ends. There's always more to explore, always more to understand. And the universe is stranger than we ever imagined, stranger than we probably can imagine. Our brains evolved to deal with medium-sized objects moving at medium speeds. They weren't designed for quantum mechanics or curved space-time or the origin of the universe. And yet we've made progress, remarkable progress. We've figured out so much, starting from so little, just by looking carefully, thinking hard, and testing our ideas against reality. That's the power of science. That's the power of curiosity and honesty and persistence. I want to leave you with a thought, a feeling really. When I look up at the night sky and see those pinpoints of light, those are suns, each one a furnace of nuclear fire, millions or billions of times more massive than the Earth. And those suns have planets probably. Some of them might have life. We don't know yet, but maybe. And beyond those stars are more stars, billions of them, in our galaxy alone. And beyond our galaxy, billions more galaxies, each one an island universe of billions of stars. And all of it, made of the same atoms that I'm made of, following the same laws, part of the same cosmos. We're not separate from the universe, we're part of it. We're the universe looking at itself, trying to understand itself. What could be more wonderful than that? What does it mean for something to move? You might say, well, it changes position. It goes from here to there. That seems obvious. But position relative to what? If you're sitting in a train and the train is moving smoothly, you might not feel like you're moving at all. You can pour a cup of coffee just as easily as you could at home. If the windows were covered, you'd have no way of knowing you were moving. But someone standing on the platform, watching the train go by, would say you're definitely moving. From their point of view, you're zooming past at high speed. So who's right? Are you moving or not? The answer is both. Motion is relative. You can only talk about motion relative to something else. There's no absolute motion, no absolute rest. This was understood even before Einstein. Galileo knew it. Newton knew it. It's sometimes called Galilean relativity. But Newton also believed in absolute space. He thought there was some fixed background, some stage on which everything happens, even if you couldn't detect it directly. He believed that even though you couldn't tell if you were moving at a constant velocity, there was still a fact of the matter about whether you were really moving relative to this absolute space. Einstein swept that away. There is no absolute space. There's no preferred reference frame, no fixed background, just objects moving relative to each other.
Well, that's almost true. Let me be more careful. Galileo's principle of relativity says that the laws of mechanics are the same for any observer moving at constant velocity. If you're in a smoothly moving train, you can do physics experiments and get the same results as someone on the ground. Einstein extended this to all of physics, not just mechanics, but everything, including light, including electromagnetism. And that leads to something strange, something Galileo couldn't have anticipated. You see, there was a puzzle about light. Light is an electromagnetic wave. It travels at a certain speed, about 300,000 kilometers per second, very fast. But if motion is relative, what is that speed relative to? If you're moving toward a light beam, shouldn't you measure it going faster? If you're moving away, shouldn't it be slower? That's what you'd expect from common sense. That's how speeds normally add up. If you're on a train moving at 50 miles per hour and you throw a ball forward at 20 miles per hour, someone on the ground sees the ball going 70 miles per hour. Speeds add, but light doesn't work that way. And this is where Einstein made his great leap. Einstein said, the speed of light is the same for all observers. No matter how fast you're moving, no matter what direction, you always measure light traveling at the same speed. That sounds impossible. It violates common sense. How can everyone measure the same speed for light regardless of their own motion? The answer is, time and space are not what we thought they were. If the speed of light is the same for everyone, something has to give. And what gives is our intuition about time and space. When you move fast, time slows down for you. Your clocks run slow compared to clocks that aren't moving. This isn't a mechanical effect. The clocks aren't malfunctioning. Time itself runs slower. Also, when you move fast, lengths contract. Objects shrink in the direction of motion. Again, not because of any mechanical stress. Space itself is compressed. These effects are called time dilation and length contraction. They're tiny at ordinary speeds. You'd never notice them in everyday life. But as you approach the speed of light, they become dramatic. Let me give you an example. Suppose you get in a spaceship and travel to a star 4 light years away, moving at 90% the speed of light. From the point of view of someone on Earth, the trip takes a little over 4 years. 4 light years at 90% the speed of light. Call it 4.5 years. But from your point of view, time is running slow. Your clocks, your heartbeat, your aging, all of it is slowed down. For you, the trip takes less than 2 years. When you arrive at the star, you're 2 years older. But back on Earth, 4.5 years have passed. This isn't science fiction. It's been tested. We've put precise clocks on airplanes and satellites, and they run at different rates than clocks on the ground. The differences are tiny, nanoseconds, but they're real. They match Einstein's predictions exactly. If you have a fast enough spaceship, time dilation is dramatic. An astronaut traveling at high speed could return to Earth and find that centuries have passed, while only years have passed for them. It's not immortality. It's not stopping time. You still age. You still experience time passing at a normal rate from your own perspective. But compared to those you left behind, compared to the rest of the universe, you've jumped into the future.
Now you might wonder, if I'm moving vital to you, I say your clocks are running slow. But from your point of view, I'm the one moving. So you say, my clocks are running slow. How can both be true? How can we each say the other's clocks are slow? This seems like a contradiction, but it's not. It has to do with the fact that simultaneity is also relative. What happens at the same time in one reference frame doesn't happen at the same time in another. This gets complicated. The resolution involves carefully thinking about how you compare clocks that are far apart and how signals travel between them. When you work through the details, there's no contradiction.
both observers are right in their own reference frame. The theory I've been describing is called special relativity. It deals with observers moving at constant velocities relative to each other. No acceleration, no gravity. When you add acceleration and gravity, things get more complicated. That's general relativity, which we talked about earlier. Curved space-time, mass warping the geometry of space and time. But even special relativity, just dealing with constant velocities, already has these strange consequences. Time dilation, length contraction, the relativity of simultaneity. There's one more thing I want to mention about special relativity. It's probably the most famous equation in physics. Energy equals mass times the speed of light squared. What does that mean? It means mass and energy are equivalent. They're two forms of the same thing. A particle at rest has energy just by virtue of having mass. This is called rest energy, and it's enormous. The speed of light squared is a huge number, so even a tiny amount of mass corresponds to a tremendous amount of energy. This is why nuclear reactions release so much energy. When you fuse hydrogen into helium, the helium has slightly less mass than the hydrogen you started with. A tiny bit of mass disappears, but that tiny bit of mass converted to energy is enough to power the sun. When you split uranium atoms, the fragments have slightly less mass than the original atom. The missing mass becomes energy. That's what powers nuclear reactors and nuclear bombs. Mass and energy are interchangeable. They're different aspects of the same thing, and this equivalence is a direct consequence of special relativity. Now, so I want to step back and think about what all this means. We started with a simple question: how do things move? And we've ended up with a radical revision of our understanding of space and time. Space is not a fixed stage. Time is not a universal clock. They're woven together into space-time, which is flexible and dynamic. Different observers slice space-time differently. What looks like pure space to one observer looks like a mixture of space and time to another. And this isn't just philosophy, it's physics. It has measurable consequences. We've tested it again and again, and nature agrees with Einstein. Why didn't we notice this before? Why did Newton's physics work so well for so long? Because the effects are small at ordinary speeds. Time dilation and length contraction depend on the ratio of your speed to the speed of light, and the speed of light is enormous. 300,000 kilometers per second. At everyday speeds, even airplane speeds, even rocket reduces. This ratio is tiny. The relativistic effects are negligible. Newton's physics is an excellent approximation. But when you get close to the speed of light, the approximation breaks down. You need Einstein. Here's a thought. Newton's laws were developed in the 1600s. For over 200 years, they were considered the ultimate truth about motion. Absolute space, absolute time, forces causing accelerations. Then Einstein came along and said, actually, that's not quite right. Here's a deeper theory.
Does that mean Newton was wrong? In a sense, yes. His theory isn't exactly right, but in another sense, no.
Newton's theory works perfectly well for most purposes. It got us to the moon. It's still used today for most engineering calculations. Newton's theory is a limiting case of Einstein's. When speeds are low compared to light, when gravity is weak, Einstein's equations reduce to Newton. The new theory contains the old one as an approximation. This pattern happens again and again in physics. A theory works well within a certain domain. Then we push to new regimes, higher speeds, smaller scales, stronger gravity, and the old theory breaks down. A new theory is needed, and the new theory typically contains the old one as a limiting case. Classical mechanics works great for everyday objects, but at atomic scales, you need quantum mechanics. At high speeds, you need relativity. Both quantum mechanics and relativity contain classical mechanics as limiting cases. So we don't throw out old theories, we understand their limits. We see where they fit into the bigger picture. And here's the thing,
We don't have the final theory yet. We know quantum mechanics and general relativity are both excellent theories in their respective domains, but they don't fit together. When you try to apply them both at once, in situations where both quantum effects and strong gravity matter, our current theories give nonsense. This happens at the center of black holes. It happens at the very beginning of the Big Bang. It happens at scales smaller than about 10 to the minus 33 centimeters, the Planck scale. At those scales, we need a theory of quantum gravity, a theory that combines quantum mechanics and general relativity. We don't have it yet. String theory is one attempt. Loop quantum gravity is another. There are other approaches. Brilliant people are working on this, but we don't have the answer. So we're in an interesting situation. We have two incredibly successful theories, quantum mechanics and general relativity. And we know they can't both be exactly right because they contradict each other in extreme situations. Something deeper is needed. Something that will contain both of them as limiting cases, the way Einstein's theory contains Newton. What will that deeper theory look like? I don't know. Nobody knows. But finding it, that's one of the great challenges of physics, one of the great adventures still ahead. Let me now talk about something different. Let's talk about how we know things, about the nature of scientific knowledge. Science is not a collection of facts. It's a process, a method for finding out how nature works. The method is simple in principle. You observe, you guess, you test your guess against new observations. If it fails, you try a new guess. If it works, you keep it, tentatively, knowing that future observations might require you to modify it. The key word there is test. Every scientific idea must be testable. It must make predictions that could, in principle, be wrong. If an idea doesn't make testable predictions, it's not science. This is what distinguishes science from other ways of knowing. Science is self-correcting. If we're wrong, eventually we find out. The universe tells us. And we are often wrong. That's okay. Being wrong is part of the process. What matters is that we're willing to be corrected. Now, scientific knowledge is never absolutely certain. We don't prove things in science the way you prove things in mathematics. In math, you start with axioms and derive theorems by pure logic. If the axioms are true and the logic is valid, the theorems are necessarily true. Science doesn't work like that. We observe nature, we see patterns, we propose laws that describe those patterns, but we can never be sure the patterns will continue. We can never be sure our laws are exactly right. Newton's laws were considered certain for 2 centuries. Then Einstein came along. Our best current theories might be replaced by something better.
But this uncertainty is not a weakness. It's a strength. It's what makes science open to new discoveries. If we were certain, we'd stop looking. We'd stop questioning. We'd become dogmatic. And dogma is the death of inquiry. So we hold our theories lightly. We believe them because they work, because they make accurate predictions, because they explain what we observe. But we're ready to revise them if the evidence demands it. There's something else I want to say about science, about honesty. A scientist must be ruthlessly honest, especially with themselves. If an experiment contradicts your favorite theory, you can't ignore it. You can't pretend it didn't happen. You have to face it. This is hard. We're human. We get attached to our ideas. We want to be right. But nature doesn't care what we want. Nature does what it does. Our job is to find out what that is, not to make nature conform to our wishes. There's a kind of integrity required, a willingness to follow the evidence wherever it leads, even if it leads somewhere uncomfortable, even if it overturns ideas you've spent years developing. The best scientists I've known have this quality. They're curious, they're skeptical, they're honest. They want to understand, not to be right. And they take pleasure in being proven wrong. Because being proven wrong means you've learned something. You've gotten closer to the truth. Let me tell you a story. When I was working on quantum electrodynamics, the theory of how light and matter interact at the quantum level, there was a period when the calculations gave infinite answers.
nonsense answers. We would calculate the mass of an electron, and we'd get infinity. We'd calculate other properties, and we'd get infinity. It was very discouraging. Some people thought the whole theory was wrong. Maybe quantum mechanics and relativity couldn't be combined after all. But eventually, we figured it out. There was a procedure. We called it renormalization that let us extract sensible, finite answers from the calculations. The infinities were there, but they canceled out in a very particular way. And when we did the calculations right, the answers agreed with experiment to 10 decimal places. 10 decimal places. That's like measuring the distance from New York to Los Angeles and being accurate to less than the width of a human hair. So the theory works spectacularly well. But is it the final answer? No. There are still things we don't understand. The procedure of renormalization is a bit, it's a bit ad hoc. It works, but we don't fully understand why it works. And quantum electrodynamics is just one piece of the puzzle. We need to combine it with the other forces, with gravity, into a unified whole. That work is still ongoing. You know, physics is often presented as a finished subject. Here are the laws, here are the equations. Learn them and you understand the universe. But that's not how it feels from the inside. From the inside, it feels like we're just scratching the surface. Every question we answer reveals 10 more questions. Every mystery we solve deepens other mysteries. The universe is not a puzzle to be completed. It's an infinite frontier to be explored. And that's exciting. That's what makes it fun. If we knew everything, what would be left to do? But we don't. We're far from knowing everything. There's so much left to discover. What is dark matter? What is dark energy? How do you combine gravity with quantum mechanics? What happened at the Big Bang? Is there life elsewhere in the universe? Are there other universes? These are big questions. Maybe some of them don't have answers. Maybe some of them are the wrong questions to ask. But asking is how we learn. Let me talk a little about the relationship between physics and other sciences. Physics is often considered the most fundamental science. Chemistry can, in principle, be derived from physics. The behavior of atoms and molecules follows from quantum mechanics and electromagnetism. Biology, in turn, is built on chemistry. The molecules of life, DNA, proteins, all of it, they obey the laws of chemistry which follow from physics. So in some sense, physics underlies everything. If you knew all the laws of physics and could solve the equations, you could, in principle, predict everything that happens, from the motion of galaxies to the thoughts in your brain.
But in practice, it's not that simple.
The equations are too complicated to solve. Even with the most powerful computers, you can't simulate a brain atom by atom. You can't predict what a person will do by solving quantum equations.
So we need other sciences. Chemistry develops concepts, elements, compounds, reactions that are useful even though they could, in principle, be derived from physics. Biology develops concepts, cells, genes, organisms, evolution, that make sense of living systems. Each level of description has its own vocabulary, its own principles, its own explanatory power. Physics doesn't replace chemistry. Chemistry doesn't replace biology. They complement each other. And there's something else. Even if we knew all the fundamental laws, there would still be surprises. Complex systems can exhibit behaviors that aren't obvious from the underlying laws. Water is made of hydrogen and oxygen atoms. If you knew everything about hydrogen and oxygen, could you predict that water would be wet? That it would form droplets? That it would be essential for life? Maybe in principle. But in practice, these properties emerge from the interactions of many atoms. They are not obvious from the laws that govern individual atoms. Emergence is a deep concept. Complex patterns arising from simple rules. Life arising from chemistry. Consciousness arising from neurons. Maybe the universe arising from something even simpler. We don't fully understand emergence. We don't have a theory of it, but we see it everywhere. The whole is more than the sum of its parts. Higher levels of organization have their own rules, their own patterns, their own behaviors. So where does physics fit in this picture? Physics gives us the foundation, the basic laws that everything else builds on. Without physics, we couldn't understand why atoms behave the way they do, why stars shine,
why the universe expands. But physics alone isn't enough. To understand complex systems, to understand life, mind, society, we need other tools, other concepts, other sciences. The universe is one thing, but we need many ways of looking at it, many levels of description, many languages. And here's a thought that I find beautiful. All those levels, atoms, molecules, cells, organisms, minds, societies, they're all part of the same universe, made of the same stuff, following the same fundamental laws. There's a unity there, a coherence. Everything is connected to everything else, not in some mystical way, but in a physical way, through the interactions of particles and fields, through causation and correlation. We're part of that unity. We're not separate from nature. We're natural. We're physical. We're made of atoms, forged in stars, evolved over billions of years, and yet we can understand. We can figure out how it all works, or at least some of it. That's remarkable. Let me end this part with a reflection. Science has taught us many things. It's taught us that the Earth is not the center of the universe, that we evolved from simpler life forms, that our minds are the product of our brains, that the universe is vast and old and mostly empty. Some people find these truths diminishing. They make us seem small and insignificant, but I don't see it that way. I find them exhilarating. Yes, we're small compared to the universe, but we contain multitudes. There are more atoms in your body than stars in the observable universe. You're inconceivably complex. Yes, we're brief compared to the age of the cosmos, but we're here now. We're conscious now. That's not nothing. And we can understand. A bit of matter organized just so, and it can contemplate the stars, can figure out quantum mechanics, can write poetry, can love. That seems like a miracle to me. Not a supernatural miracle, but a natural one. The universe has produced, through blind processes, beings that can appreciate it, that can understand it, that can wonder at it. What more could we ask for? Now, I want to talk about something that puzzles me, something that puzzles everybody who thinks about it carefully: quantum mechanics. We've touched on it before, but let's go deeper, because quantum mechanics is not just another theory. It's not just a refinement of classical physics. It's a completely different way of thinking about reality. And honestly, nobody fully understands it. Not really. We know how to use it. We know how to calculate with it. The predictions are spectacularly accurate. But what it means, what it tells us about the nature of reality, that's still debated. Let me start with something concrete. The double slit experiment again. I know we talked about it, but it's so important that it's worth revisiting. You have a barrier with two slits. You shoot particles at it, electrons, photons, whatever. On the other side, you have a screen that records where the particles land. If you cover one slit, you get a simple pattern. Particles go through the open slit and spread out a bit, making a blob on the screen. If you open both slits, you'd expect to just get two blobs, right? One from each slit. The particles go through one slit or the other. But that's not what happens. Instead, you get an interference pattern. Bright bands where lots of particles land. Dark bands where almost none land. The pattern you'd expect from waves interfering. Okay, so maybe the particles are waves. Waves go through both slits and interfere. That would explain it. But wait, each particle lands at a definite spot on the screen. A single point. That's particle behavior. Waves don't land at points. They spread out continuously. So which is it? Wave or particle? Here's where it gets really strange. If you send the particles through one at a time, with big gaps between them, so there's never more than one particle in the apparatus at a time, you still get the interference pattern. Eventually, each individual particle lands at a definite spot, but over many particles, the spots build up into the interference pattern. Each particle somehow interferes with itself. It goes through both slits at once, even though it's a single particle, even though it lands at a single spot. How can one particle go through two slits? It doesn't make sense in ordinary terms. A particle should take one path or the other, not both. But quantum mechanics says, it's not like that.
The particle doesn't have a definite path until you measure it. Before measurement, it's in a superposition of all possible paths. It goes through both slits. It goes through neither. It goes through each one. All of these and none of these are true. I know that sounds like nonsense, but it's what the experiments tell us, and the experiments don't lie. Now, what happens if you try to find out which slit the particle goes through? What if you put a detector at the slits to watch? If you do that, the interference pattern disappears. You just get two blobs. The particles start acting like particles again, going through one slit or the other. The act of observing, of measuring which path the particle takes, changes the outcome. When you don't look, you get interference. When you look, you don't. This is deeply disturbing. It suggests that observation plays a special role in physics, that reality is, in some sense, dependent on whether we're watching. But what counts as an observation? Does it have to be a conscious observer? Or does any physical interaction count? These questions have been debated for almost a century, and there's still no consensus. Some interpretations of quantum mechanics say that observation causes the wave function to collapse. The superposition of possibilities suddenly becomes a single, definite outcome. But what triggers the collapse? Why should observation be special? Other interpretations say there is no collapse. All the possibilities continue to exist in parallel branches of reality. When you observe which slip the particle went through, you become entangled with the particle, and different versions of you see different results. The many worlds interpretation. I don't know which interpretation is right. Maybe none of them are. Maybe we need completely new concepts that we haven't thought of yet. What I do know is that quantum mechanics works. The math gives predictions, and the predictions match experiment. Whatever is really happening at the quantum level, the theory captures it well enough to be useful. And maybe that's all we can ask for. Maybe demanding a picture, a visualization, an intuitive understanding. Maybe that's asking for something the universe doesn't provide. You can create two particles in a special state, an entangled state, where their properties are correlated. For example, two electrons whose spins are correlated. If you measure one and find it spinning clockwise, the other is guaranteed to be spinning counterclockwise, and vice versa. That might not sound strange. Maybe the electrons had those spin directions all along, and we just didn't know until we measured. But quantum mechanics says no. Before measurement, neither electron has a definite spin direction. They're both in superpositions. The correlation exists, but the individual values don't. Here's the weird part. You can separate the entangled electrons by a large distance, miles apart, light years apart in principle. Then you measure one. Instantly, the other one has a definite spin, the opposite of what you measured. How does the second electron know what happened to the first? How does the information get there? Einstein hated this. He called it spooky action at a distance. He thought it proved that quantum mechanics was incomplete, that there must be some hidden variables, some underlying reality that we weren't seeing. But experiments have tested this very carefully, and the results are clear. There are no hidden variables of the kind Einstein imagined. The correlations are real and irreducible. Entanglement is genuine. Now, I should be careful here. Entanglement doesn't let you send information faster than light. Even though the correlation is instantaneous, you can't use it to communicate. The results on each side look random until you compare them. And comparing them requires ordinary communication, which is limited to the speed of light. So relativity is safe, causality is preserved. But still, there's something deeply non-local about quantum mechanics. The universe is connected in ways that classical physics never imagined. What does it mean? I don't know. Nobody knows. But it's one of the things that makes quantum mechanics so fascinating and so frustrating. We have this incredibly successful theory, and we don't know what it's telling us about reality. Let me shift gears and talk about something else. The atoms that make up matter. How do they work? What determines their properties? This is where quantum mechanics really shines. It explains atoms. It explains chemistry. It explains why the periodic table has the structure it does. An atom has a nucleus, protons and neutrons, surrounded by electrons.
The electrons are attracted to the nucleus by electrical forces, but they don't just fall in. Quantum mechanics keeps them out. Remember the uncertainty principle? If you confine an electron to a small region, its momentum becomes uncertain. It has to be moving around rapidly. That motion gives it kinetic energy. So there's a balance. The electrical attraction pulls the electron toward the nucleus. The uncertainty principle gives it energy that resists confinement. The electron settles into an equilibrium, a certain average distance from the nucleus. But it's not just one possible state. There are many. Different energy levels, different shapes of probability distributions. We call them orbitals. The electron can be in the lowest energy state, or it can be excited to a higher state if it absorbs energy. When it falls back down, it emits energy as light. This is where atomic spectra come from. Each element has a unique set of energy levels and therefore a unique set of colors it can emit or absorb. That's how we identify elements in distant stars. We look at their light. Now here's something beautiful. The periodic table of elements, that whole structure, it follows from quantum mechanics. Electrons fill up the available energy states. They start with the lowest energy states and work their way up. But there's a rule, the Pauli exclusion principle, that says no two electrons can be in exactly the same state. So the electrons stack up, first one in this state, then one in that state. When all the states at one energy level are filled, the next electron has to go to a higher level. The chemical properties of an element depend mostly on its outermost electrons, the ones in the highest energy levels. These are the electrons that interact with other atoms. Elements with similar outer electron configurations have similar chemistry. That's why the periodic table is arranged the way it is. Elements in the same column have similar properties. Lithium, sodium, potassium, they're all in the first column. They all have one electron in their outermost shell. They're all highly reactive, eager to give up that electron to form bonds. Helium, neon, argon, they're in the last column. They have full outer shells. They're stable. They don't easily react with anything. All of chemistry, all the reactions and compounds and molecules, it all comes from quantum mechanics, from the behavior of electrons in atoms, and therefore all of biology too. DNA is a molecule, proteins are molecules, life is chemistry, and chemistry is quantum mechanics. I find that astonishing. The same quantum rules that govern a single electron in a hydrogen atom, they scale up to explain the entire complexity of life. Not that we can calculate it all. The equations are too complicated. But in principle, it's all there. The laws that govern a hydrogen atom are enough to determine that carbon can form long chains, that water has its peculiar properties, that DNA can carry genetic information. From simple rules, enormous complexity emerges. Let me tell you about nuclear physics now. What's inside the nucleus? The nucleus is made of protons and neutrons. Protons are positively charged, neutrons are neutral. They're held together by a force called the strong nuclear force. The strong force is very strong, hence the name, but it has a short range. It only acts over distances comparable to the size of a nucleus. Beyond that, it falls off rapidly. This is very different from gravity or electromagnetism, which reach out over infinite distances. Now here's a puzzle. Protons are all positively charged. They repel each other electrically. How does the nucleus hold together? The answer is the strong force. It's attractive and much stronger than the electrical repulsion, as long as the particles are close enough. But this creates a limit. If you put too many protons in a nucleus, the electrical repulsion starts to win. The nucleus becomes unstable. It tends to break apart or emit particles. This is radioactivity. Unstable nuclei decaying into more stable configurations. There are different kinds of radioactive decay. Alpha decay, where the nucleus emits a helium nucleus, 2 protons and 2 neutrons. Beta decay, where a neutron turns into a proton by emitting an electron. Gamma decay, where the nucleus emits high-energy light. In all cases, the nucleus is moving toward a more stable state, releasing energy in the process. Some elements are naturally radioactive. Uranium, for example. Its nucleus has 92 protons. That's a lot. The electrical repulsion is barely held in check by the strong force. Uranium nuclei are unstable. They decay over time. The rate of decay is characterized by the half-life, the time it takes for half of a sample to decay. For uranium-238, the half-life is about 4.5 billion years. For other isotopes, it can be fractions of a second. Radioactive decay is a quantum process. You can't predict when a specific nucleus will decay. It's random, probabilistic. All you can say is the probability of decay in a given time period. This was disturbing to some people, Einstein among them. He famously said, "God does not play dice." But experiment after experiment has confirmed, yes, nature does play dice. At the quantum level, outcomes are genuinely random, not just unpredictable because we lack information, but fundamentally, irreducibly random. Now let's talk about nuclear energy. We mentioned it before, but let's go deeper. When light nuclei fuse together, they release energy, hydrogen fusing to helium. This is what powers the sun. When heavy nuclei split apart, they also release energy, uranium or plutonium breaking into smaller pieces. This is nuclear fission. This is what powers nuclear reactors and bombs. In both cases, the products have slightly less mass than the starting materials. The missing mass becomes energy, lots of energy. That famous equation again.
Nuclear energy is incredibly concentrated. A kilogram of uranium contains as much energy as thousands of tons of coal. This is both a blessing and a curse. It means we can generate enormous amounts of power from small amounts of fuel. But it also means we can create devastating weapons. The same physics that could solve our energy problems has created the threat of nuclear war. This is the duality of science. Knowledge is power, and power can be used for good or ill. The science itself is neutral. It's up to us how we use it. Let me tell you about something smaller still. Inside protons and neutrons, there are quarks. For a long time, protons and neutrons were considered fundamental particles, indivisible. But in the 1960s, experiments showed that they have internal structure. They're made of smaller things. A proton is made of 3 quarks, 2 up quarks and 1 down quark. A neutron is also 3 quarks, 1 up and 2 down. Quarks are strange particles. They have fractional electric charges. An up quark has positive 2/3 of the electron's charge. A down quark has negative 1/3. 3 of them combine to give the proton its charge of positive 1. And quarks are never found alone. They're always confined inside particles, like protons and neutrons. If you try to pull a quark out of a proton, the energy required becomes enormous. Instead of freeing the quark, you create new quark-antiquark pairs. The quarks stay confined. This is called confinement. It's a property of the strong force. The force between quarks doesn't decrease with distance. It stays constant, or even increases. So you can never isolate a single quark. The theory of quarks and the strong force is called quantum chromodynamics, QCD. It's one of the pillars of the Standard Model of particle physics. The Standard Model is our best current theory of fundamental particles and forces. It includes quarks, electrons, neutrinos, photons, gluons, W and Z bosons, and the Higgs boson. It describes 3 of the 4 fundamental forces: electromagnetism, the weak force, and the strong force. Gravity is not included. We don't have a quantum theory of gravity that fits into the Standard Model. The Standard Model is incredibly successful. Its predictions have been confirmed to extraordinary precision, but we know it's not complete. It doesn't explain dark matter. It doesn't explain why there's more matter than antimatter. It doesn't include gravity. It has about 20 parameters, numbers like particle masses and force strengths, that have to be put in by hand, determined by experiment, rather than predicted by the theory. There should be something deeper, something that explains the Standard Model, something that answers these open questions. What might that deeper theory be? We don't know. String theory is one candidate. It proposes that fundamental particles aren't points, but tiny vibrating strings. Different vibration patterns correspond to different particles. String theory is mathematically beautiful, but it's very difficult to test. It makes predictions at energy scales far beyond what we can probe with current experiments. Other approaches exist. Loop quantum gravity, causal set theory. Each has its advocates. None has been confirmed. This is the frontier, the edge of knowledge. Beyond here, we don't know, and that's okay. That's how science works. We push into the unknown. We make guesses. We test them. Some guesses pan out. Most don't. Slowly, painstakingly, we extend the boundaries of what we know. It's taken us 400 years to get from Newton to the Standard Model. Where will the next 400 years take us? I have no idea. And that's part of the excitement. Let me step back and talk about something more philosophical. What is the universe made of? We've talked about particles, electrons, quarks, photons. These are the building blocks in the Standard Model. But there's another way to think about it. Fields. A field is something that has a value at every point in space and time, like the temperature field. At every location, there's a temperature. Or the pressure field in the atmosphere, or the gravitational field around the Earth. In quantum field theory, particles are excitations of underlying fields. The electron is an excitation of the electron field. The photon is an excitation of the electromagnetic field, and so on. When there are no particles, the fields are still there. They're in their ground state, their lowest energy state, but they're not zero, they're fluctuating. This is the quantum vacuum, empty space. It's not really empty. It's filled with fields in their ground states, constantly fluctuating. Remember the uncertainty principle? It applies to fields too. You can't have a field that's perfectly still. There must be some uncertainty, some fluctuation. These vacuum fluctuations are real. They have measurable effects. The Casimir effect, where two metal plates close together feel a tiny force pushing them together. That's a vacuum fluctuation effect. So the vacuum is not nothing. It's something, a seething sea of quantum fluctuations. And here's a wild thought. The vacuum has energy, 0-point energy, the energy of all those fluctuations. When you calculate how much energy this should be, using straightforward quantum field theory, you get an absurdly large number, far larger than anything we observe. This is one of the biggest puzzles in physics, the cosmological constant problem. Our theories predict that empty space should have enormous energy density. But when we look at the universe, we see that the vacuum energy is either zero or incredibly tiny. Something is wrong. Either our calculation is wrong, or there's something we're missing, some mechanism that cancels most of the vacuum energy. We don't know what it is. This is one of the great unsolved problems, and it might be a clue to new physics. You know, the more we learn, the more we realize how much we don't know. That might sound discouraging, but I find it liberating. It means there's always more to discover, always another mystery to pursue. The universe is not a closed book. It's an open frontier, and we're the explorers. Newton gave us a picture of gravity as a force. The sun pulls on the earth pulls on the moon. Objects attract each other across empty space. But Newton himself was uncomfortable with this. He wrote that gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance through a vacuum, without the mediation of anything else, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. In other words, Newton didn't believe his own theory, not fully. He knew it worked, but he didn't understand how one object could affect another across empty space with nothing in between. Einstein solved this puzzle, but his solution was radical. He said, there is no force of gravity. Not really. What we call gravity is actually the curvature of space-time. Let me try to explain what that means. Imagine you're an ant living on a flat piece of paper. You can walk around, draw lines, measure distances. Your world is two-dimensional and flat. Now imagine someone takes that paper and bends it, curves it. From your ant perspective,
The paper might still seem flat locally. If you only look at a small region, it looks the same as before. But if you make careful measurements over larger distances, you'd find something strange. You might draw what you think is a straight line, the shortest path between 2 points, and find that it's actually curved. You might draw a triangle and find that the angles don't add up to what they should. You might walk in what you think is a straight line and end up back where you started. The geometry of your world would be different, not Euclidean, curved. Einstein said our universe is like that. Space-time, the four-dimensional fabric that combines space and time, is curved by the presence of mass and energy. Near a massive object like the sun, space-time is curved, and objects moving through this curved space-time follow curved paths. They're not being pushed or pulled by a force. They're following the straightest possible paths through a curved geometry. These paths are called geodesics.
Think about it this way. On the surface of the Earth, the straightest path between 2 points is a great circle, an arc. If you fly from New York to Tokyo, you don't go in what looks like a straight line on a flat map. You curve up over the Arctic. But that curved path is actually the shortest distance on the curved surface of the Earth. Objects in a gravitational field are doing the same thing. They're following the shortest paths through curved space-time. Those paths happen to look like falling or orbiting, but there's no force involved, just geometry. This is a beautiful idea. Gravity is geometry. The motion of planets, the fall of apples, the bending of light near stars, it's all geometry. And it makes specific predictions that differ from Newton, not by much in most cases, but in extreme situations, near black holes in the early universe, with very precise measurements, the differences are detectable. Every time we've tested Einstein against Newton, Einstein wins. Nature prefers geometry to force. Now, let me try to make this more concrete. How does mass curve space-time? Einstein gave us an equation. A very complicated equation. It relates the curvature of space-time to the distribution of mass and energy. I won't write the equation because, well, it involves tensors and differential geometry, and it would take hours to explain properly. But the basic idea is this. Matter tells space-time how to curve, and curved space-time tells matter how to move. It's a dynamic relationship. The mass creates the curvature guides the motion. And if the mass moves, the curvature changes too. Everything affects everything else. One of the predictions of general relativity is gravitational waves, ripples in space-time itself. If you have massive objects moving around, like 2 stars orbiting each other, they stir up the space-time around them. They create waves that propagate outward at the speed of light. These waves are incredibly weak. Even a violent event like 2 stars colliding produces gravitational waves that by the time they reach Earth stretch and squeeze space by less than the width of a proton. But we've detected them. In 2015, for the first time, we directly observed gravitational waves from 2 black holes merging. The detection required instruments of almost unbelievable precision, but it worked. Einstein was right, yet again. Gravitational waves open a new window on the universe. For most of history, we've studied the cosmos using light, visible light, radio waves, X-rays, all forms of electromagnetic radiation. But gravitational waves are different. They're not light. They're ripples in space-time itself. They pass through matter like it's not there. They come from events that might not produce much light, like black hole mergers. It's like, imagine you've been deaf all your life, and suddenly you can hear. A whole new sense, a whole new way of perceiving the world. That's what gravitational wave astronomy is, a new sense for the universe. Speaking of black holes, let's talk about them. A black hole is a region of space-time where gravity is so strong that nothing can escape. Not matter, not light, nothing. How does this happen? Well, imagine compressing mass into a smaller and smaller region. The gravitational field at the surface gets stronger and stronger. At some point, the escape velocity, the speed you'd need to leave the surface, reaches the speed of light. And since nothing can travel faster than light, nothing can escape. You've created a black hole.
The boundary of a black hole is called the event horizon. It's not a physical surface. You wouldn't feel anything special if you crossed it. But once you're inside, you can't get out. From the outside, the event horizon is a one-way boundary. Information can fall in, but it can't come out. Whatever is inside is hidden from the rest of the universe. What happens inside a black hole? Honestly, we don't know. Our equations break down. According to general relativity, everything that falls into a black hole gets compressed toward a point of infinite density at the center, a singularity. But infinite density doesn't really make physical sense. It probably means our theory is incomplete. This is one of the places where we need quantum gravity, a theory that combines general relativity with quantum mechanics. Whatever happens at the center of a black hole, we need new physics to describe it.
Black holes sound exotic, but they're actually quite common in the universe. There are stellar black holes, formed when massive stars collapse at the end of their lives. They're typically a few times the mass of the sun. And there are supermassive black holes at the centers of galaxies, millions or billions of times the mass of the sun. Our own Milky Way has one. It's about 4 million solar masses. How did supermassive black holes form? We're not sure. They might have grown from smaller black holes that merged over time, or they might have formed in different ways in the early universe. This is an active area of research. Let me tell you something strange about black holes. They're not completely black. In the 1970s, Stephen Hawking discovered that black holes emit radiation, very faintly. This is called Hawking radiation. The radiation comes from quantum effects near the event horizon. Remember those vacuum fluctuations we talked about? Pairs of particles constantly popping into existence and then annihilating each other? Near the event horizon, something special can happen. One particle of a pair can fall into the black hole while the other escapes. The escaping particle carries energy away from the black hole. Over time, this causes the black hole to lose mass and shrink. For large black holes, this effect is incredibly tiny. A stellar black hole would take far longer than the age of the universe to evaporate. But for small black holes, it could be significant. And Hawking radiation raises a deep puzzle: information. When something falls into a black hole, what happens to the information it carried? If the black hole eventually evaporates completely, where does that information go? According to quantum mechanics, information can't be destroyed. It can be scrambled and hidden, but not destroyed. Yet if the black hole evaporates into featureless thermal radiation, the information seems to be lost. This is the black hole information paradox, and it's still not resolved. Some of the brightest minds in physics have worked on it for decades. There are proposed solutions, but no consensus. This is what I mean when I say physics is not finished. We have these incredible theories, general relativity, quantum mechanics, and where they overlap, we find contradictions, puzzles, paradoxes. The universe is telling us something. There's deeper truth we haven't found yet. Let me now talk about something vast, the structure of the universe as a whole. On the largest scales, the universe is remarkably uniform. In every direction we look, we see roughly the same thing. Galaxies distributed in a cosmic web, clusters and superclusters connected by filaments, with vast voids in between. This uniformity is called the cosmological principle. On large enough scales, the universe looks the same everywhere. No special places, no special directions. This uniformity is actually puzzling. Different parts of the universe are very far apart. So far apart that light hasn't had time to travel between them since the Big Bang. How did distant regions end up looking so similar? They've never been in contact. They couldn't have coordinated. The standard answer is inflation, a period of extremely rapid expansion in the very early universe. Before inflation, regions that are now far apart were actually very close together. They had time to reach equilibrium. Then inflation stretched them apart, faster than light. Wait, faster than light? Isn't that impossible? Nothing can travel through space faster than light. But space itself can expand at any rate. During inflation, space expanded exponentially. Regions were carried apart faster than light could travel between them. This doesn't violate relativity.
because nothing is moving through space faster than light. Space itself is stretching. It's a loophole in the cosmic speed limit. Inflation also explains something else, the geometry of the universe. Space can be curved, as we discussed. It can be positively curved, like the surface of a sphere, or negatively curved, like a saddle, or flat. When we measure the geometry of the universe using the cosmic microwave background and other observations, we find that it's flat, or very nearly flat. As far as we can tell, space is not curved on large scales.
That seems like a coincidence. Why should the universe be flat rather than curved? But inflation provides an answer. Inflation stretched the universe so much that any initial curvature was flattened out, like inflating a balloon until it's so big that the surface looks flat. So inflation solves several puzzles at once. The uniformity of the universe, its flatness, and it even provides a mechanism for the tiny fluctuations that grew into galaxies. But what caused inflation? What drove this rapid expansion? The standard answer is a quantum field called the inflaton. In the early universe, this field was in an unstable state with lots of energy. That energy drove the expansion. Eventually, the field decayed, releasing its energy and reheating the universe. But we don't know what the inflaton field is. We haven't detected it. It's a placeholder for our ignorance. You know, cosmology is like archaeology. We're trying to reconstruct the past from the traces it left behind. The cosmic microwave background is our best photograph of the early universe. It's a snapshot from 380,000 years after the Big Bang, when the universe first became transparent. Before that, we're mostly guessing. We have theories, we have models, but we don't have direct observations. And the further back we go, the less certain we become. The first fraction of a second after the Big Bang, we're extrapolating our physics into regimes where it's never been tested. What happened at the very beginning? The moment of the Big Bang itself? We don't know. Our equations give singularities, infinities, nonsense. This probably means our theories break down. Maybe there was no beginning. Maybe time is eternal. Maybe the Big Bang was just a transition from some previous state. Maybe there are other universes. Maybe the question doesn't even make sense. We don't know, and we might never know. Some questions might be beyond the reach of science. But that doesn't mean we stop asking. Asking is how we learn. Even if some questions have no answers, the attempt to answer them teaches us things. Let me talk about something humbling, the scale of the universe. The observable universe is about 93 billion light years across. That's the part we can see. Light from beyond that hasn't had time to reach us. But the universe might be much larger, infinitely larger perhaps. We don't know. Within the observable universe, there are roughly 2 trillion galaxies. Each galaxy contains billions of stars. That's something like a septillion stars, a 1 with 24 zeros after it. And most of those stars probably have planets. We've discovered thousands of exoplanets already. They seem to be common. Is there life elsewhere? Intelligent life? We don't know. We've never detected it. But the numbers are staggering. So many stars, so many planets. It seems unlikely that Earth is the only place where life arose. But where is everyone? If intelligent life is common, why haven't we seen any signs of it? This is the Fermi paradox. Maybe intelligent life is rare. Maybe civilizations destroy themselves before they spread across the galaxy. Maybe they're out there, but we haven't looked hard enough. Maybe they're avoiding us. Maybe they're so different we wouldn't recognize them. We don't know. It's one of the great open questions. The search for extraterrestrial life is ongoing. We listen for radio signals. We look for signs of technology. We send probes to other planets and moons in our solar system. Mars might have had life once. Europa, a moon of Jupiter, has an ocean under its ice that might harbor life. Enceladus, a moon of Saturn, shoots geysers of water into space that might contain microbes. We're looking. So far, nothing. But we've barely begun to search. Whether or not there's life elsewhere, the universe is magnificent, vast and ancient and beautiful. Stars being born in clouds of gas, stars dying in violent explosions, galaxies colliding and merging over billions of years, black holes consuming matter and warping space-time, neutron stars spinning hundreds of times per second, cosmic rays traveling for millions of years before striking our atmosphere. It's a spectacular show, and we have front-row seats. Let me tell you about time again. We've talked about how time is relative, how it flows at different rates in different situations. But there's more. Time has a direction. Things happen in a certain order. The past is different from the future. This seems obvious, but it's actually mysterious. The fundamental laws of physics are mostly time-symmetric. If you film a simple interaction and play it backward, the backward version also obeys the laws of physics. Yet we experience a clear arrow of time. We remember the past, not the future. Causes precede effects. Entropy increases.
The arrow of time seems to come from the second law of thermodynamics. Entropy, disorder, tends to increase. Systems evolve from less probable states to more probable states. An egg can break, but a broken egg doesn't spontaneously reassemble. Not because the laws forbid it, but because it's overwhelmingly unlikely. There are vastly more ways for the egg to be broken than intact. So the arrow of time is statistical. It emerges from the behavior of large numbers of particles, not from the fundamental laws themselves. But this raises a question. Why did the universe start in a low entropy state? If high entropy is more probable, why wasn't the early universe in equilibrium? This is one of the deepest mysteries. The early universe was hot, but it was also extremely uniform. That uniformity represents low entropy in a gravitational sense. Why? We don't know. Some cosmologists think it has to do with inflation. Others think it might be explained by a deeper theory of quantum gravity. Others think it might be a selection effect. Only low entropy beginnings lead to observers who can ask the question. Time is strange. We feel like we're moving through it from past to future. But physics doesn't really support that picture. In relativity, time is just another dimension, like space. Past, present, and future all exist. The flow of time might be an illusion, a feature of consciousness rather than reality. Or maybe not. Maybe there's something we don't understand about time. Maybe the physics is incomplete. I don't know. Nobody knows. But it's fascinating to think about. Let me say something about the relationship between physics and reality. Physics gives us models, mathematical structures that describe how things behave. These models are incredibly successful. They make accurate predictions. They allow us to build technology. But are the models reality? Or are they just descriptions of reality? This is a philosophical question, and physicists disagree about it. Some are realists. They believe our models capture something true about the world. Electrons really exist. Space-time really is curved. Others are more cautious. Models are tools, they say. They work, but that doesn't mean they're pictures of reality. We shouldn't take them too literally. I lean toward realism myself. When a theory makes predictions that are confirmed to 10 decimal places, it's hard to believe it's not onto something real. But I hold my realism lightly. The history of physics is full of discarded theories that seemed true at the time. What we can say for sure is this: nature has patterns, regularities, laws. Whatever ultimate reality is, it's not chaos. It's not arbitrary. There's structure there, and that structure is accessible to us. We can discover it. We can understand it, at least partly. That's remarkable. That's what makes science possible. So, we've covered a lot of ground: atoms and quantum mechanics, relativity and space-time, the structure of the universe, the nature of physical law. Let me now try to pull some of this together to see the big picture. What have we learned about the universe? What does physics tell us about reality? First, the universe is comprehensible. Not completely, not yet, but to a remarkable degree. The same laws that govern a falling apple also govern the motion of galaxies. The same quantum mechanics that explains a hydrogen atom also explains the fusion reactions in the sun. There's a unity to nature, a coherence,
Everything fits together. Second, the universe is strange. It doesn't behave like common sense would predict. Time is relative. Particles can be in two places at once. Empty space seethes with energy. Black holes warp space-time so severely that nothing can escape. Our intuitions, developed for survival on the African savanna, don't apply to the very fast, the very small, or the very massive. To understand those realms, we have to abandon intuition and follow the mathematics.
Third, the universe is vast and old. Billions of galaxies, each containing billions of stars. A history stretching back nearly 14 billion years. Distances so large that light takes billions of years to cross them. We're tiny, a speck on a speck orbiting a speck in the suburbs of an ordinary galaxy. From a cosmic perspective, we barely exist. And yet we can comprehend all this. We can figure out how stars work, how galaxies form, how the universe began. Our minds can encompass when our bodies cannot.
Fourth, the universe is not finished revealing itself. We don't know what dark matter is. We don't know what dark energy is. We don't know how to combine gravity with quantum mechanics. We don't know what happened at the Big Bang. There are deep mysteries waiting to be solved, discoveries waiting to be made. The adventure of science continues. Let me talk about something that I think is underappreciated, the role of simplicity in physics. The fundamental laws are simple, not easy. The mathematics can be challenging, but simple in the sense of economical. A few principles, a few equations, and from them you can derive an enormous range of phenomena. Newton's laws of motion, 3 laws. From them you can understand everything from billiard balls to rocket ships to planetary orbits. Maxwell's equations, 4 equations. From them, all of electromagnetism, light, radio waves, the behavior of circuits, the forces that hold atoms together. The Schrödinger equation, 1 equation. From it, the structure of atoms, the periodic table, the behavior of semiconductors, the chemistry of life. Why should the laws be simple? Why should a handful of equations describe so much? We don't know. It didn't have to be this way. The universe could have been complicated. Different rules in different places. New laws needed for each new phenomenon. But that's not what we find. We find unification. We find that apparently different phenomena are aspects of the same underlying reality. Electricity and magnetism seem separate. Maxwell unified them. Space and time seem separate. Einstein unified them. The electromagnetic force and the weak nuclear force seem separate. They've been unified too. This gives physicists hope. Maybe everything can be unified. Maybe there's a single theory, a single set of equations from which all of physics follows. We call this hypothetical theory a theory of everything. We don't have it yet, but the pattern of unification suggests it might exist. String theory is one candidate. It proposes that all particles are vibrations of tiny strings. Different vibration modes give different particles. The theory naturally includes gravity. It's mathematically beautiful, but string theory is hard to test. It makes predictions at energy scales far beyond our current experiments. We can't verify it directly, so we don't know if string theory is right. It might be, it might not be, it might be partially right. Time will tell. Even if we find a theory of everything, that won't be the end of physics. Knowing the fundamental laws doesn't mean you can predict everything. The laws of chess are simple. A few rules for how pieces move, but that doesn't mean you can easily predict who will win a game. The complexity is emergent. Similarly, even if we knew the final laws of physics, we'd still have work to do. Understanding how complex systems behave, how life emerges, how minds work, how galaxies evolve. Physics would continue, just at a different level. Let me talk about something personal. Why do I find physics so fascinating? Partly it's the puzzle solving. There's a problem. You think about it. You try different approaches. And sometimes, if you're lucky, something clicks. You see the answer. That feeling of understanding, there's nothing quite like it. But it's more than that. It's the sense of touching something real, something true, something that was true before humans existed and will be true after we're gone. When I understand a piece of physics, I feel connected to the universe in a deep way. I'm not just a passive observer, I'm a participant. I'm the universe understanding itself. You know, science is often seen as cold, impersonal, just facts and equations. But that's not how it feels from the inside. Science is a deeply human activity, full of passion and creativity and wonder. The best scientists I've known are not calculating machines, they're dreamers. They're artists in their own way. They see beauty in equations, elegance in theories, poetry in the structure of reality. Einstein didn't discover relativity by grinding through calculations. He imagined himself riding on a beam of light. He asked what the universe would look like from that perspective. The mathematics came later.
Imagination is essential. The ability to think beyond what's known, to consider possibilities that haven't been considered before.
But imagination alone isn't enough. You also need discipline, rigor, the willingness to test your ideas against reality and abandon them if they fail. That's the balance of science. Creative enough to think of new ideas, humble enough to let nature judge them. Let me tell you about uncertainty. I've mentioned it several times, but I want to emphasize it. Scientific knowledge is never absolute. It's always provisional, always subject to revision. Newton's mechanics was considered certain for 2 centuries. Then Einstein showed it was approximate. Our current theories might be replaced by something better. This isn't a weakness, it's a strength. Science is self-correcting. If we're wrong, we can find out. We can fix our mistakes. Dogma doesn't allow that. Dogma says, here is the truth, accept it, don't question. Science says, here is our best current understanding. Test it, challenge it, improve it. And there's another kind of uncertainty, the uncertainty of what we don't know. We don't know what dark matter is. We don't know how consciousness arises from neurons. We don't know if there's life elsewhere in the universe. We don't know what happened before the Big Bang. These are open questions. Maybe they'll be answered someday, maybe not. But acknowledging them is important. Science is not a collection of facts. It's a process, a way of asking questions and seeking answers. The questions we haven't answered yet are as much a part of science as the answers we have. Let me say something about the relationship between science and other ways of knowing. Science is powerful. It's given us technology, medicine, an understanding of the cosmos. But it's not the only way to understand the world. Art explores human experience in ways science doesn't. Literature illuminates the human condition. Philosophy asks questions that science can't answer, about meaning, about ethics, about the nature of knowledge itself. Science tells us how the universe works. It doesn't tell us how to live. It doesn't tell us what's valuable. It doesn't tell us what we should do. Some people see a conflict between science and other ways of knowing, especially between science and religion. I think that conflict is often exaggerated. Science answers different questions than religion does. Science asks how. Religion asks why, or whether there even is a why. You can be a scientist and be religious. Many are. You can be a scientist and be an atheist. Many are. Science doesn't dictate your metaphysics. What science does require is honesty, a willingness to follow the evidence, a commitment to truth over comfort. But here's something important. The methods of science, observation, hypothesis, testing, these methods have been extraordinarily successful in their domain. They've revealed truths about nature that we couldn't have discovered any other way. If you want to know about atoms, you do physics. If you want to know about stars, you do astronomy. If you want to know about life, you do biology. There's no shortcut, no alternative method that works as well. So while science isn't the only way of knowing, it's the best way of knowing certain things. The things it's good at, it's very good at. Let me talk about the future. What might we discover? In particle physics, we might find new particles, particles that make up dark matter, particles that explain why there's more matter than antimatter. The Large Hadron Collider and its successors will keep searching. In cosmology, we'll get better maps of the cosmic microwave background, better measurements of the expansion of the universe. Maybe we'll detect gravitational waves from the Big Bang itself. In quantum physics, we're building quantum computers, machines that exploit quantum superposition and entanglement to do calculations that classical computers can't. They might revolutionize cryptography, drug discovery, material science. We might detect life elsewhere, on Mars, on the moons of Jupiter and Saturn, on exoplanets around other stars. Even microbial life would be momentous. It would tell us that life is not unique to Earth.
We might understand consciousness. How does a brain, a collection of neurons, give rise to subjective experience? This is one of the hardest problems in science, but neuroscience is advancing rapidly. We might unify physics, find that final theory, that theory of everything. Or we might discover that the universe is more complicated than we thought, that there are layers of reality we haven't imagined. What won't we discover? That I can't tell you. The most important discoveries are usually surprises, things we didn't expect, things we couldn't have predicted. That's what makes science exciting. We don't know what's coming next. Let me return to something I said at the beginning, the atomic hypothesis. All things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. That one sentence, it contains an enormous amount of information about the world. If you understand it deeply, you understand much of physics and chemistry and biology. And the amazing thing is, it's true, or at least, it's a very good approximation to the truth. Atoms are real. They behave roughly as I described. But atoms aren't the end of the story. Atoms are made of smaller things, electrons, protons, neutrons. Protons and neutrons are made of quarks. And quarks and electrons might be made of something smaller still, strings perhaps, or something we haven't discovered. There are layers, levels of description. Each level has its own concepts, its own laws, its own domain of applicability. At the everyday level, we talk about tables and chairs and people. At the chemical level, we talk about molecules and reactions. At the atomic level, electrons and nuclei. At the particle level, quarks and leptons and bosons. At the deepest level, we don't know yet. Each level emerges from the one below. Tables are made of molecules. Molecules are made of atoms. Atoms are made of particles. But each level has its own reality, its own patterns, its own regularities. You can't understand psychology just by studying quarks. The levels are too far apart. Emergence creates genuine novelty at each level. So even if we find the final theory, the theory of the deepest level, we'll still need all the other levels. We'll still need chemistry and biology and psychology and economics. Each level describes real patterns that matter. The universe is like a vast tapestry, woven from threads that follow simple rules. But the patterns that emerge, the galaxies and stars and planets and life, those patterns are rich beyond imagination. We're part of that tapestry, threads in the cosmic weave, made of star stuff, governed by the same laws that govern everything else, and yet conscious, aware, able to ask questions, able to understand. That's the miracle. Not a supernatural miracle, a natural miracle. The universe has produced, through blind processes, beings that can appreciate it. As I think about all this, the vastness of space, the depth of time, the strangeness of quantum mechanics, the elegance of the laws, I feel something like awe. Not religious awe necessarily, but awe nonetheless. A sense of wonder at the sheer fact that anything exists at all, that there's something rather than nothing, that the something is ordered and beautiful and comprehensible. Why is there something rather than nothing? I don't know. Maybe the question doesn't make sense. Maybe nothing is impossible. Maybe the universe had to exist. Or maybe it's just a brute fact. No explanation. It just is. We've come a long way, from caves to telescopes, from myriad to physics, from ignorance to, well, less ignorance. But we're still at the beginning, still scratching the surface, still children in a vast universe we barely understand. And that's okay. That's more than okay. That's wonderful. The adventure continues. The questions keep coming. The universe keeps surprising us. What more could we want?
Ask it a question the right way, and it will answer. That's what experiments are. Questions asked of nature, and nature always answers. Sometimes the answer is surprising.
Sometimes it overturns everything you thought you knew, but it's always an answer. There's a kind of integrity to that, a trustworthiness. The universe plays fair. I find that comforting somehow. In a world full of uncertainty and confusion, there's this bedrock of reality that you can rely on. The laws of physics don't change because someone's having a bad day. They don't bend to power or wealth or popularity. They just are. Let me tell you what I think physics is really about. It's not about equations. It's not about memorizing formulas. It's not about getting the right answer on a test. It's about understanding, really understanding, grasping how things work in your bones, being able to think about a problem and see, really see, what must happen and why. When you understand something deeply, you don't need to memorize it. It becomes obvious. Of course that's how it works. How could it be any other way? That feeling, that click of understanding, it's one of the best feelings there is. It's why I do physics. Not for the fame or the prizes, for that moment when something that was confusing suddenly makes sense. And here's the beautiful thing. You can have that feeling too. Anyone can. You don't need to be a genius. You just need to be curious, patient, willing to think. The universe is there for everyone. Its secrets are open to anyone who takes the time to look. Now, I want to say something about doubt, about uncertainty, about not knowing. We've talked a lot about what we know, but what we don't know is just as important, maybe more important. Science progresses by admitting ignorance, by saying, I don't know, but let's find out. That takes courage. It's much easier to pretend you know, to make up an answer, to accept what someone tells you, but pretending doesn't get you anywhere. Only honest inquiry does. Only the willingness to be wrong, to be surprised, to change your mind when the evidence demands it. I don't know what dark matter is. Nobody does. I don't know how to combine gravity with quantum mechanics. Nobody does. I don't know what happened at the very beginning of the universe. Nobody does. And that's okay. That's good, actually. It means there's still work to do, still discoveries to make, still surprises waiting. If we knew everything, what would be the point? The joy is in the finding out, the journey, not the destination. Let me tell you about something that matters to me, the freedom to doubt. Throughout history, people have been punished for questioning accepted beliefs, burned at the stake, imprisoned, exiled. Even today, in some places, you can get in trouble for asking the wrong questions. But science requires the freedom to doubt, to question everything, to follow the evidence wherever it leads, even if it leads somewhere uncomfortable. That freedom is precious. It's not guaranteed. It has to be defended. Every generation has to fight for it again.
And it's not just about science. The freedom to think, to question, to doubt, that's essential for any free society, for any progress, for any genuine understanding. Dogma is the enemy. Certainty is dangerous. The people who are most sure they're right are often the most wrong. Humility is a virtue, intellectual humility, the recognition that you might be mistaken, that there's always more to learn, that the universe is bigger than your understanding of it. So, what should you take away from all this? What's the message? I don't want to be preachy. I don't want to tell you what to think. That would defeat the whole point. But maybe this. The universe is wonderful, strange and vast and beautiful, and you're part of it, made of the same stuff as stars, governed by the same laws as galaxies. You have the capacity to understand. Not everything, but something. And that something can grow. Every question you ask, every puzzle you solve, expands the horizon of what you know. Don't be afraid of not knowing. Embrace it. Revel in it. The unknown is not a threat. It's an invitation. And don't be afraid of being wrong. Being wrong is how you learn. Every scientist has been wrong many times. The good ones admit it and move on. What matters is the pursuit, the honest,
humble, passionate pursuit of understanding. That's what science is. That's what life can be. You know, God sometimes think about all the people who came before us, all the curious minds who looked at the world and wondered, the ancient Greeks who first conceived of atoms, the medieval scholars who kept learning alive through dark times, Galileo peering through his telescope at the moons of Jupiter, Newton watching an apple fall and wondering about the moon, Darwin contemplating the tangled bank of life, Einstein reimagining space and time, all the nameless students and teachers and tinkerers who contributed their small pieces to the great puzzle. We're part of that tradition, that chain of curiosity stretching back millennia. Every question we ask connects us to everyone who's ever asked questions. And the chain continues forward, too, into the future, to people who aren't born yet, who will ask questions we can't imagine, who will discover things we can't conceive. We're a link in that chain, a moment in that ongoing conversation. What we learn, we pass on. What we discover, we share. The knowledge grows. That's a kind of immortality, isn't it? Not personal immortality, but the immortality of understanding. The things we figure out will still be true long after we're gone. Let me say something about beauty, the beauty of physics. The equations are beautiful. The symmetries are beautiful. The way everything fits together is beautiful. But it's not just aesthetic beauty. It's the beauty of truth, of glimpsing something real, something deep, something that underlies everything. When you see a sunset, it's beautiful. But when you understand why the sky is red, when you know about the scattering of light and the composition of the atmosphere and the angle of the sunset becomes more beautiful, not less. Understanding doesn't diminish wonder, it enhances it. The more you know, the more there is to wonder at. I've spent my life chasing that wonder, trying to understand, and I'm not done. I'll never be done. There's always more. And that's the point, I think. The endless unfolding, the infinite frontier, the questions that lead to more questions. Let me try to sum up. What have we learned? Matter is made of atoms. Atoms are made of smaller things. Those smaller things obey quantum mechanical rules that defy common sense. Space and time are woven together and curved by mass and energy. The universe began in a hot, dense state and has been expanding ever since. There's dark matter and dark energy that we don't understand. The laws of physics are mathematical, symmetrical, and universal. That's quite a lot. Centuries of work by thousands of brilliant people condensed into a few sentences. But it's also just the beginning, a sketch, an outline. Behind every sentence is a world of detail, of nuance, of unsolved problems.
And beneath all the details, there's this mystery, this fundamental mystery. Why is there something rather than nothing? Why does the universe exist at all? Why is it comprehensible? Why is there beauty in the laws? I don't know. I don't think anyone knows. Maybe these questions don't have answers. Maybe they're not the right questions. But I love that they can be asked. I love that we're the kind of creatures who ask them, who look up at the stars and wonder, who take things apart to see how they work, who aren't satisfied with easy answers. You're that kind of creature too. You wouldn't have listened this long otherwise. So, keep asking, keep wondering, keep doubting and questioning and exploring. The universe is there, waiting, patient, ready to reveal its secrets to anyone curious enough to look. It's late now, or early, depending on how you count. The stars are out there, burning. Galaxies are spinning. Atoms are jiggling. Quantum fields are fluctuating. Time is flowing, or not flowing, we're not quite sure. And you're here, a collection of atoms, improbably arranged, somehow conscious, somehow curious, somehow aware of it all. That's remarkable. That's the most remarkable thing, I think. I think the universe is lucky to have observers. Not because observing changes anything in a mystical sense, but because what good is all this beauty
if no one appreciates it? What good are the laws if no one understands them? We're the universe's way of knowing itself, of appreciating itself, of marveling at its own elegance. That's not nothing. That's something. Well, I suppose I should let you sleep now. That was the point of all this, wasn't it? To help you drift off? I hope I haven't kept you too awake with all this talk of black holes and quantum mechanics and the origin of the universe. Those aren't exactly soothing topics. But maybe understanding is soothing in its own way. Knowing that the universe makes sense, that there's order beneath the chaos, that the same laws that govern the stars govern you. You're not alone. You're connected to everything, part of the cosmic tapestry made of ancient atoms forged in stravel of fires, carrying on the long tradition of curiosity and wonder. The night is quiet now. The questions can wait until tomorrow. There will always be more questions, more mysteries, more things to figure out. But for now, rest. Dream of atoms dancing, of light bending around stars, of space stretching and time dilating, of quantum possibilities branching and collapsing, of the vast cosmic web of galaxies strung like jewels across the darkness. Dream of understanding, of that click when something makes sense, of the beauty of a simple equation that explains a complex world. Dream of the universe, because you are the universe, dreaming of itself.
I think the universe is lucky to have observers. Not because observing changes anything in a mystical sense, but because what good is all this beauty if no one appreciates it? What good are the laws if no one understands them? We're the universe's way of knowing itself, of appreciating itself, of marveling at its own elegance. That's not nothing. That's something. You know what strikes me? How improbable all of this is. The constants of nature, the strength of gravity, the charge of the electron, the mass of the proton. If any of them was slightly different, we wouldn't be here. Stars wouldn't form, or they'd burn too fast, or atoms wouldn't hold together, or chemistry wouldn't work. The universe seems tuned, finely tuned, for complexity, for life, for minds. Why? Is it luck? Are there other universes with different constants where nothing interesting happens? Or is there something deeper going on? I don't know. Nobody knows. But it's remarkable that we can even ask the question. Let me tell you something about discovery, about how it feels. Most of the time, science is frustrating. You're stuck. Nothing works. Your ideas are wrong. You feel stupid. But then, sometimes, there's this moment, this flash. Suddenly you see it. The pieces come together. What was confusing becomes clear. What was complicated becomes simple. That feeling, there's nothing like it. It's like the universe just whispered a secret to you, and you're the first person to hear it. That's why we do this. Not for the fame, not for the prizes, for that moment of understanding, that glimpse behind the curtain. And here's the thing. You don't have to be a professional scientist to experience that. Anyone can. A child looking through a magnifying glass. A student suddenly understanding calculus. Someone lying in bed thinking about the stars. The universe doesn't care about your credentials. It reveals itself to anyone who looks carefully enough. So, what have we learned tonight? Let's see. Matter is made of atoms. Atoms are mostly empty space. The solid world is an illusion created by electromagnetic forces. Light is both a wave and a particle, depending on how you look at it. Literally. Time is not absolute. It flows differently depending on how fast you're moving and how close you are to massive objects. Space is not a fixed stage. It curves and bends and stretches. Gravity is geometry. The universe began in a hot, dense state and has been expanding ever since. It's 14 billion years old. It contains hundreds of billions of galaxies, each with hundreds of billions of stars. Most of the universe is made of stuff we don't understand. Dark matter, dark energy, 95% mystery. Quantum mechanics rules the small world, and it's deeply strange. Particles in two places at once, observation affecting reality, uncertainty built into the fabric of nature. And through all of this, through all the strangeness and vastness and complexity, there's order. There are patterns, there are laws, the same physics everywhere, the same rules for everything, a unity beneath the diversity. That's beautiful. I don't know how else to say it. It's beautiful. You know, I've spent my whole life thinking about these things, and I'm still amazed, still surprised, still delighted by what we find. Every answer opens up new questions. Every discovery reveals new mysteries. The more we know, the more we realize we don't know. Some people find that frustrating. I find it wonderful. It means the adventure never ends. Let me tell you about something that happened to me once. I was sitting in a cafeteria, just eating lunch, and I saw a plate wobbling. Someone had thrown it in the air like a frisbee, and it was wobbling as it spun. And I noticed something. The wobble and the spin had a certain relationship. The plate wobbled twice for every rotation. Now, this is completely useless information. Who cares about wobbling plates? But I couldn't let it go. I had to figure out why. So I went back to my office and I worked it out. The equations of motion, the relationship between wobble and spin. And I got it. I understood why. And that led to thinking about rotating systems in general, which led to thinking about electrons, which led to, well, to work that eventually won me a prize. But that's not the point. The point is, I wasn't trying to win anything. I was just curious about a wobbling plate. The curiosity led somewhere unexpected. That's how science works. You follow your curiosity. You ask questions about things that seem trivial, and sometimes you stumble onto something profound.
The universe rewards curiosity. Not always immediately, not always obviously, but eventually. So stay curious. Ask questions. Wonder about things, even small things, especially small things. Why is the sky blue? Why does water form droplets? Why do mirrors reverse left and right, but not up and down? Why do you feel heavier in an elevator that's accelerating upward? These questions have answers, beautiful answers, answers that connect to deep truths about nature. I want to say something about humility. The more I learn about the universe, the more humble I feel. We're so small, so brief, so limited in our understanding. And yet we figured out so much. From our tiny vantage point on this speck of dust, we've deduced the age of the cosmos, the structure of atoms, the history of stars. That's remarkable. But it should make us humble, not proud. We've climbed a few hills, but the mountains stretch endlessly ahead. There's so much we don't know,
So much we may never know. The honest answer to most deep questions is still, we don't know. And that's okay. That's good, actually. Certainty is the enemy of discovery. Doubt is the engine of progress. Let me tell you about the future. Not predictions. I can't predict the future. But possibilities. Things that might happen. Questions that might be answered. We might find life elsewhere. On Mars, on Europa, on a planet around another star. Even microbial life would be revolutionary. It would mean life is not a fluke. It happens wherever conditions allow. We might understand consciousness, how matter becomes mind, how neurons create experience. That would change everything. Philosophy, religion, technology, all transformed. We might unify physics, find that final theory, the one that explains everything, the quantum theory of gravity, the theory of everything. Or we might discover that there is no final theory, that nature has layers all the way down, turtles on turtles on turtles. We might travel to other stars. Not soon, not easily. The distances are vast and the challenges immense. But it's not impossible. Nothing in physics forbids it. Imagine that. Humans, or whatever we become, spreading through the galaxy, carrying life and mind to other worlds. The universe waking up bit by bit. That's a future worth working toward. A future worth dreaming about. But those are far-off dreams. What about now? What about tomorrow? Tomorrow, someone will make a discovery. Somewhere in the world, in a lab or an observatory or a classroom, someone will figure something out. A small piece of the puzzle will click into place. It might be a professional scientist. It might be a student. It might be an amateur astronomer in their backyard. It might be you. Because that's the thing about the universe. It doesn't care who you are. It responds to honest inquiry. It rewards genuine curiosity. You don't need permission to wonder. You don't need a degree to ask questions. You just need to pay attention, to think carefully, to not be satisfied with easy answers. So, where does that leave us? We're atoms that have learned to think, star stuff that has become conscious, a tiny part of the universe that has woken up and started asking questions.
What I'm about to reveal could be the difference between an ordinary life and an extraordinary one. There are 6 lessons that can turn any mind into a machine that learns fast, thinks clearly, and achieves the impossible. These aren't tricks. They're codes the greatest geniuses used to see what others couldn't. Those who master these lessons truly learn, craft solutions that change everything, and reach levels that once seemed out of reach. Pay close attention now. These 6 lessons aren't just knowledge. They are the key to unlocking your mind and completely changing your destiny. Lesson 1. Curiosity is the key to success. Stop everything and pay attention. Everything you've achieved so far, from your very first words to your most important victories, was born from a single impulse: curiosity. Curiosity is the spark that has moved humanity since the beginning of history. It pulled us out of caves, helped us master fire, led us to create language, science, and technology, and even to explore space. What brought us here was curiosity, a natural talent we all carry within us, but many allow to fall asleep. Here's the key. While most people are satisfied to accept things as they are, the curious ask why. That's how Thomas Edison, standing in the dark, refused to believe the world was meant to live by candlelight and asked, "What if I could create a controlled light?" And that's how another thinker looked up at the sky,
and refused to accept the simple idea that time and space were fixed. He asked, what if time could bend? What if the speed of light is the key that connects everything in the universe? From that boldness came the theory of relativity, one of the most revolutionary discoveries in history, redefining what we thought we knew about reality.
Do you see the power in this? While millions go through life repeating ready-made truths, a few dare to question. Lose your curiosity, and you lose your future. Because curiosity keeps your mind young, alive, restless, and ready to find paths others can't see. Curiosity is more valuable than any diploma, more powerful than any talent, and rarer than any resource. It is the fuel of great innovators, entrepreneurs, and leaders. Let today be a turning point. Never again allow your curiosity to be smothered by routine, fear, or the opinions of others. From now on, instead of accepting ready-made answers, choose to question. No matter how silly the questions seem, don't stay silent in the face of doubt. Dare to ask. The curious don't just learn more, they live more, achieve more, and build a life that seems impossible to those who lost the ability to ask. Lesson 2. The secret is thinking differently from the crowd. Pay close attention now, because you're about to hear something no one ever told. You don't need to be the smartest person in the room to stand out. You don't need to memorize more information, have the highest IQ, or master every detail. If you simply learn to think differently from the majority, you already have a massive. The world is full of talented people who stay average because they think like everyone else. But those who dare to look from another angle, question what seems obvious, and choose their own path, those are the ones who rise. There are thousands of people studying every day, going to college, collecting diplomas, trying to outthink others to secure a better future. And yet, an ordinary person without titles or status can have the courage to create something that doesn't exist yet. And suddenly, that person becomes more valuable than all the scholars combined.
Power doesn't come only from the knowledge you accumulate, but from the vision to give the world what it does not yet have. That's how inventors, entrepreneurs, and creators change the game. Not by being the most technically intelligent, but by daring to think differently. Here is the real secret. Thinking differently doesn't require genius. It requires courage. Courage to reject ready-made answers. Courage to go against the crowd. Courage to look strange or even wrong for a while. That's why innovators, entrepreneurs, and visionaries stand out. They dared to think where others wouldn't. Now, here's something that can change your life. Train your mind every day to flip common logic. When everyone says, "It can't be done," ask, "How can it be done?" When everyone goes right, ask, "What's on the left?" When everyone sees a problem, ask, "Where is the opportunity?" This ability, more than intelligence, more than talent, is what separates those who follow the crowd from those who create their own destiny. Lesson 3. Turn mistakes into learning. Pay close attention. A mistake is a master in disguise. Most people run from it as if it were proof of failure, but true winners embrace it as an endless source of wisdom. Every time you make a mistake, life is handing you a clue, a map of where not to go, how to improve, how to refine. The electric light, which seems obvious today, was born from thousands of failed attempts. Its inventor famously said, "I have not failed 1,000 times. I've simply found 1,000 ways that don't work." That mindset is the difference between those who quit and those who conquer. Here's a powerful secret. Mistakes accelerate learning far more than successes do. Getting it right reinforces what you already know. Getting it wrong reveals what you didn't know. It's like a lens that shows, with clarity, exactly where you need to grow. Those who have the courage to fail fast and learn fast always surpass those who try to live without failing. Now think about your own life. How many times have you blamed yourself for a mistake,
What if, instead, you started seeing each failure as a lab, a controlled experiment that becomes the foundation for a stronger next step? Never again treat a failure as the end. Treat it as the beginning of something greater. A mistake is simply life saying, not this way. There's another path. If you have the courage to listen, you'll discover that every stumble is actually an invitation to rise higher. Lesson 4. Talk to yourself to learn. Explain to learn. If you truly want to master any subject, reading, listening, or memorizing isn't enough. The secret is to explain. The human mind works in a fascinating way. When you try to explain something out loud, even to yourself, it's forced to organize ideas, fill in gaps, and simplify concepts. In that process, learning becomes real clarity. The smartest people aren't the ones who memorize facts. They're the ones who can convey an idea so clearly that even a child understands it. If you can't explain it simply, you haven't truly understood it. That is the ultimate proof of learning. Here's something that can change your life. Make this a daily discipline. Whenever you learn something new, stop and explain it out loud as if you were teaching someone who has never heard of it. If clarity is missing, go back and study again until you can simplify. Do this consistently, and before long, your mind will become sharp like a blade, able to cut any confusion into pieces. While most people fool themselves into thinking they've learned because they can recite information by heart, you'll be different. Someone who understands, masters, and applies. Explain to learn, and the world will notice the difference in how you speak, decide, and solve problems. Lesson 5. Simplify to the essence. The true test of intelligence isn't to complicate, it's to simplify. If you really want to learn anything, you must master the art of simplicity. Most people make the mistake of thinking knowledge means piling up fancy words, memorizing technical terms, or repeating complex phrases. That isn't intelligence, that's vanity. Real intelligence is taking something complex and reducing it to its essential core. Use this test every time you learn something new. If I had to explain this to a 10-year-old, how would I do it? If you can't answer, you don't understand it yet. The confusion is in your mind, and simplicity is the tool that clears the excess. Think of history's great breakthroughs. Gravity expressed in a short formula. Evolution captured in a single idea. The best adapted survive. Even the world's biggest businesses can be described in a simple sentence. Connect people. What does this prove? When you reach the essence, you own the knowledge. Understand this. Simplifying isn't making it shallow. Simplifying is digging deeper until you find the solid bedrock that supports everything else. That's where your mind gains clarity, and where you prove to yourself that you've truly learned. Make it a daily practice. Take any subject and boil it down to a few words. If you can't, go back and study until you can. This habit will change how you think, speak, and act. People who explain with clarity are heard. Those who speak simply are remembered. Those who deliver essence are followed. While most try to look smart by complicating, you'll be different. The person who illuminates, resolves, and teaches. And that ability will make your mind stand out anywhere in the world. Lesson 6. The beauty of life's simplicity. True greatness isn't in accumulation. It's in seeing the beauty of the essential. Imagine this. A life where you don't need to prove anything to anyone. Where you're not trapped by comparisons or the frantic race of the crowd. That's where true peace lives. Not in knowing everything, not in achieving everything, but in valuing what truly matters. The greatest sages and thinkers in history shared one thing. They saw greatness in simple things.
They were moved by a flower, by the movement of the stars, by the way a child asks questions. They knew life doesn't need to be complicated to be grand. The simpler you live, the more room you create for happiness. Simplify your thoughts, your goals, your routine. It's not about having less, it's about being more present, more grateful, more aware. That's how you find peace. That's how you find strength. That's how you find abundance. Now, make your commitment public. Comment below, "I choose to master my mind." That's the mark of someone who will no longer get lost in excess, someone ready to focus on the essential and build an extraordinary life. If this message resonated with you, like this video, subscribe, and turn on notifications. From here on out, every lesson you hear will be another tool to strengthen your mind, unlock your potential, and transform your life. Remember, real power isn't in knowing everything,